as we've said here, we've been dealing pretty much exclusively with right triangles for the entire course. Now, that's actually about to change. We're going to enter into what we call oblique triangles, which simply are triangles that do not contain a right angle. It can either have 3 acute angles or an obtuse angle with 2 acute angles. Now, in determining angle and side measurements, the ratios for the right triangles that we learned are simply not going to apply here. So we're going to learn 2 new methods of finding missing sides and angles. One of which will be the law of sines. And basically, the law of sines is the ratio of the side, which we'll call lowercases a, b, and c, to their appropriate angles. Now, you could honestly represent it like this if you really wanted to. And as to why it works, there is a very lengthy proof for it, but how about we just believe it? So that's what we're going to get. Oh, also, all right, so basically solving an oblique triangle, more or less, so basically when you are going to solve a triangle, when you're told, hey, solve this triangle, what you're simply going to do is find the lengths of all of its side and measurements of the angles. So the law of sines can be used to solve a triangle in which one side and 2 angles are known so far. So we can call this using side angle angle, and yes, there can be some profanity in here a little bit later, the angle side side congruence that you might have heard about back in your, my guess is they teach that in math too. But yeah, angle side side. But yeah, they don't really teach that. Now, think about it though. When 2 angles are known, you really know the third angle, because the fact is, all 3 angles of a triangle add up to what? 180. So you literally, as long as you're given 2 angles and any of the sides, this is a side where it's not included between the 2 angles, but technically it becomes included because you do know, when you know 2 angles, you really know all 3 angles. So for instance, what we're going to do here is we're going to find these angles and sides here. So this is little c. So the measure of angle A, well, that's going to be pretty easy. So, measure of angle A. What is the measure of angle A going to be? What do we get for that? 71 degrees. So, here's the thing. So, not only are we going to calculate what A and C are, but we're going to also kind of realize that which of these is going to be the smallest of the 3 sides? It's going to be side C, because if it's opposite the smallest angle, it's going to be the smallest side. And on the flip side, these 3 sides, which is going to be the largest? A is going to be the largest. Now, generally 2 decimals is my rule of thumb for these. So we can, basically write out the law of sines. A over sine of 71 degrees. But notice that I'm replacing things with what I know. 19 over the sine of 59 degrees. And it'll equal C over the sine of 50 degrees. So, conventional, some people would say, figure out what sine of 71, sine of 59, and sine of 50 are and use those in the ratios. I don't like to do it that way. What I like to do here is, in order for us to solve for side A, we'll basically just have this little ratio here, A over sine of 71 equaling 19 over the sine of 59 degrees. So we can just do a cross multiply, or as some students in my past would call it, the butterfly method. And all you have to do for that, it's literally going to be A times the sine of 59 degrees equaling 19 times the sine of 71 degrees. And in order for us to solve that for A, we divide out by the sine of 59 degrees. And we get A equal to whatever this is. Well, whatever that is, we can easily figure out using our calculator times the sine of 71. And this is where having the calculator in degree mode might actually be advantageous, but not really to me. And we get A equal to 20.96 feet. Now, it's also rather evident that, A is going to be the larger of the three sides, or the largest, I should say. So what I want you to do is find the length of side C. What you can do here is, now that we have a value for A, you could basically set any two of these equal to each other. And I would recommend just setting the second two equal to each other when you have a given side, because if we use 20.96 for A, it's going to work. Don't get me wrong, but it might give you something a little bit different. So basically, you have 19 over sine of 59 degrees equaling C over sine of 50 degrees. So using our wonderful cross multiplying again, 19 times the sine of 50 equals C times the sine of 59 degrees. And then we divide out by sine of 59 degrees. And we'll figure out what C is going to be. Oh, I'll set up a fraction here. So yeah, you have 19 times your sine of 50 degrees over the sine of 59 degrees. And that will be 16.98 feet. And obviously that's going to fit our little agenda, so to speak, because C is going to be the smallest side. So yeah, law of sines is honestly the simpler of the cases here, but especially when you're given two angles, because you are technically given a third angle. So what I want you to do is, for both of these triangles, find all your missing. Number one, if you're given two angles, it's easy enough to find the third just by doing 180 minus 80 minus 39, not 33, but 39, and that'll be 61 degrees. So if I call this B, I call this A, and I'll call this little c. So let's see here. You would have A over sine of 39 equals B over sine of 61, and that'll equal 36 over sine of 80 degrees. So basically, yeah, you're going to solve two different ratios to figure out what A and B are going to be. Well, the thing is, these practice problems are generated. All right, so let's see here. I think I'm going to go and find out what B is first. So we have B over sine of 61 equal to 36 over sine of 80 degrees. So you have B times sine of 80 equal to 36 times the sine of 61 degrees. Well, if we divide out by sine of 80, and no, you can't subtract like 61 and 80 here, but it's just going to be B, and we'll put like about equal to because but yeah, you'll see what I'm talking about here. So 36 times sine of 61 degrees over sine of 80. And that's 31.97 feet. So now we want to figure out what A is going to be. A is going to be easy. You have A over sine of 39 equal to 36 over the sine of 80. Now, technically, you could have done it as 31.97 over the sine of 61. But I don't like to do it that way because that doesn't give me the exact answer that I would get. I mean, it would be pretty darn close. But A times the sine of 80 degrees is going to be 36 times sine of 39 degrees, dividing out by sine of 80 degrees. And here's what I'll do. I'll just do this. 39. And we get 23.01 feet. And that's what we get. All right, so let's see here. So we know our missing angle is going to be, let's see, I believe 58 degrees. So if we call this A, this is side B. Side B is obviously going to be the largest. Side C is going to be the smallest. So basically you have A over sine of 58 degrees equal 33 over sine of 105, and it'll equal C over sine of 17. So we can let's figure out A. So basically you have A times the sine of 105 equaling 33 times the sine of 58 degrees, and dividing out by sine of 105, and we use our calculator to figure that out. 33 times sine of 58 degrees over sine of 105. And that'll be 28.97 centimeters. And obviously, A is going to be the middle side in terms of its length. C is going to be the smallest. So we can basically get 33 over sine of 105 equal to C over sine of 17 degrees. And again, cross multiply and simplify. That's all we really have to do. 33 times the sine of 17 degrees equals C times the sine of 105 degrees. Dividing out by 105, C will be 33 times the sine of 17 degrees over sine of 105. Oop, wrong thing. And here's the thing. Because I'm using the same ratio, similar ratio here, all I really have to do is go up and change this angle. And I'm going to get, wow, C equal to 9.99 centimeters. And yeah, most anybody, myself included, would gladly have accepted 10 centimeters for that, but that's what we get. All right, so that's the simplest version of using law of sines. Because here's the thing. It's going to get a little bit more involved here in just a few moments. Now, let's say we're given two sides and an angle, and yes, it's the angle side. Funny. Yeah. Of course, when I taught geometry as a high school teacher, we didn't do law of sines or cosines. But yeah. So here's the thing, though. What can happen here with angle side side? That's going to be known as the ambiguous case when using the law of sines. Because here's the thing. We're going to be finding a missing angle. And what's going to happen here, to simply put it, you're going to have the sine of whatever angle, A, B, or C, equal to a numeric value. And what'll happen is, technically, that could become, well, no, you will get two different angles, because basically it could be represented by first quadrant or a second quadrant angle. Now, the ambiguous case for one triangle, I mean, it's not really an ambiguous case, but for angle side side, we're always going to get two angles. And we're going to see why it might not be two triangles. It could just be one triangle. And there's even the possibility of having no triangle, which makes life a little bit easier. Because the sine of whatever could be greater than 1. So with that in mind, if we wanted to solve this particular triangle, we're going to get something, and this is when you'll have to draw it, I'm afraid. But remember, basically, measure of angle A is opposite side A. Measure of angle B is opposite side B. And measure of angle C is opposite side C. Although you probably already knew that. So even though we're going to draw it, see, this is where my drawing skills SUCK. So we'll call this 25 degrees. We'll call this angle A. And this will be 4 feet for little a. And here's the thing. We don't know which one to call B or C. But I think what appears to be the largest of the sides, let's call this one 35 foot for C, and here's measure of angle C, and then here's little b, angle B. So here's the thing. Using the law of sines, here's what's going to happen. You have 4 over the sine of 25 degrees equal to b over sine of b, there's nothing there, equaling 35 over the sine of c. So here's what's going to happen. It's very simple. Basically, you will do 4 over sine of 25 degrees equal to 35 over the sine of c. And what's going to happen here is you're going to get sine of c equal to something. And then you would use the inverse or arc sine to figure out what c is. But let's see what happens here. So you have 4 times the sine of c equal to 35 times the sine of 25 degrees. And then we divide out by 4. So sine of c is going to be 35 times the sine of 25 degrees over 4. Now, there's 2 ways that you can go about this. You can actually figure out what 35 times the sine of 25 is over 4. And when we do that, 35 times the sine of 25 degrees, come on, here we go. 35 times the sine of 25 degrees over 4, and that's going to be, 3.7. So measure of angle C would be the inverse sine of 3.7. And here's the thing. The sine of an angle can be anywhere between what 2 values? Think of the range of the parent sine function. What can it be between? Nope, you're thinking range of the inverse. Basically, a sine can be anywhere between 0 and 1. So the domain of the inverse sine has to be between -1 and +1. That's not. And if you want even, that could have been not the worst thing in the world. But if you take the inverse sine, now if you took the sine of 3.7, you'd get something, but the inverse sine of 3.7, I get a domain error, and we know that's not going to work. In fact, in mode, well, yeah. Let me just see something here before even if it's in imaginary mode. So here's the deal. There is basically no triangle. No triangle. It's going to make your life a little bit easier. Now, for the next one, now one thing you can tell, you have a lot more room on this next one. And if you know the way I do things, if you figured out the way I kind of do things here, what's going to happen is if there's more room for something, chances are there's going to be something with this. So we set up the trig ratio first. So I'll put angle C as 44 degrees. And this will be 31 feet. And I'll put 35 feet for B. And I know nothing for A. So basically you have A over sine of A equal to 35 over sine of B equal to 31 over sine of 44 degrees. So what's going to happen is you're going to get sine of B equal to something. I mean, I'm sure you learned it at home. Probably. All right, so we'll set these two equal to each other. 35 over sine of B degrees equals 31 over sine of 44. Oh, see, that's where could have had a real problem here. 35 times the sine of 44 degrees equals 31 times the sine of B degrees, dividing out by 31. So this is what sine of B is going to equal. So what you could do, there's actually really two schools of thought on this. One idea that I always would do, well, you could just do the 35 times the sine of 44 degrees. And you're going to get 0.7843. I would round that to 4 decimal places, but what's going to happen is you're going to end up taking the inverse sine of 0.7843. So, measure of angle B will be the inverse sine of 0.7843. The more decimal places you took this to, the better. So what I'm also trying to say is if you just cut it off at 2, you might get something a little bit different here. But we're going to, so let's see something here. If I took the inverse sine of this deal and convert that to an angle, convert that to degrees, it's going to be 51.66 degrees. But I want to point out something here and show you why, 4 decimal places is probably enough. If we did 0.7843, we get that times 180 and dividing it by pi. Yeah, so 4 decimal places is good. But here's the thing. The measure of angle B is going to be 51.66 degrees. But here's the thing. There is another angle. So basically, this is going to be a 2 triangle case, possibly. So here's the thing. If we're doing this with a sine, the sine can equal 0.7843 for 2 different angles. One in the first quadrant, and which is basically 51, crappy drawing. Yeah, 51.66. And one in the second quadrant, that is, this is 51.66, so you'd subtract 180. 180 minus 51.66 degrees, or measure of B would be 128.34 degrees. But we're not exactly going to solve for both triangles yet. Because right now, the one angle that you were given was 44 degrees. Now, it's a possibility that, based on the math, obviously if you added this and 44 degrees, it is not going to be larger than 180. But there's a possibility that, based on different side lengths or whatever, it might. But, So if this angle plus the existing angle that we had added up to more than 180, we would only have one triangle to solve, which is this one. But we have two triangles. So basically, based on this, we need to figure out the measurements of everything based off of measure of angle B being either 51.66 or 128.34. The measure of C is 44 degrees no matter what. But we have to figure out the measure of angle A in both of these. It is going to be different. So, well, that's easy enough to figure out. Basically, take, bless you, 180 minus 51.66 minus 44. In this case, you're going to have 84.34 degrees. And in the other case, you take 180 minus 128.34 minus 44, and we get 7.66 degrees. Now, so that's what we're going to get here. And from those, your next job is to figure out the missing side, A. Now, obviously, A is going to be a lot smaller in this one. In fact, A is going to be the smallest side in the case of this. So here's the thing. So case 1 draws it like that, and like, yeah, see, it's going to keep that same side here. So that's kind of how we could do that.
Will we do the comparison to our known value of the C ratio or the variable, the B ratio?
I would do it for the C ratio. Yeah, the one that's known. I mean, yeah, basically, so here's the thing. If you took the sine, so it wouldn't matter really. If you took the sine of 51.66 degrees, that is going to equal a certain value, not that. It's going to equal whatever that is. If you took the sine of 128.34 degrees, you would get the same thing. Now, yeah, so in reality, yeah, I mean, you could use the B. I mean, yeah, so I completely understand what you're saying. If you use the B, yeah, the sine of B is going to be the same thing no matter what. So, but that's why it all works. All right, so basically, you have A over sine of 84.34 degrees equal to 31 over the sine of 44 degrees. And let's see here. And of course, what unit of measurement is this in? It's all in feeties. I'll tell you one thing There used to be an app on the calculator. In fact, I think it still exists to where I could actually type it, if it's linked to my computer, I could actually type in on the calculator and it would show up right on here, like Smartboard or something. But I don't know if it would work with like a wireless USB transponder. So yeah, sine of 44 degrees. A is going to be 44.41 feet. That's big. Now, if we go about figuring out length of side A for this one, that's now A over the sine of 7.66 degrees equal to 31 over sine of 44. See, there's no ambiguity about the C ratio. C is C. A equals, well, 31 times the sine of 7.66 degrees over sine of 44 degrees. So I just kind of did that a little quicker than I probably should have, but let's see here. We're going to get for little a, oh, come on, 5.95 feet. So before we end it for today, yeah, basically, yeah, two triangles. So if this would be like little a here, I could call it like A prime. See how much smaller it is? But it does maintain the 35 and the 44 degree angle. And B would be obviously a lot larger than that. All right, that's where we'll stop here, folks. So have yourselves a wonderful weekend. Okay, so for this one, this is going to be a more basic law of sines deal, because we already know the measure of angle B is going to be 180 less these two, 180 minus 44 minus 38, and that's going to be 98 degrees. So if we were to actually go ahead and draw it, here is C. So this is the non-ambiguous case. 44 degrees. You know, 38 degrees and 98 degrees. So let's see here, 26 feet. So basically, we have A over sine of 38 degrees equals B over sine of 98 degrees equals 26 over sine of 44 degrees. So what I'm going to do here is what I did with the previous example, and I'm going to store my A and B. I'm going to store the missing sides here just to show you how it works. I mean, truth be told, again, all you have to do, you can just use the rounded values. So let's figure out what B is first. So you have B times the sine of 44 degrees equal to 26 times the sine of 98 degrees. We divide out by your sine of 44. And let's see here. So we figure out what that's going to be. Times the sine of 98 degrees over sine of 44 degrees. And that'll be 37.06 feet. And one thing we can do here is I'm going to go ahead and just store that to B now. Now for A, I can do, A over sine of 38 degrees equals, I could do the B one, but I'm going to do it equal to the C ratio. 26 over the sine of 44 degrees. A times the sine of 44 equals 26 times the sine of 38. And dividing out by your sine of 44 degrees. Let's see what A is going to be. So we have 26 times sine of 38 degrees over top of sine of 44 degrees. And we get A equal to 23.04 feet. And if I store that to A, that's just going to give me the most exact value. Now, do you have to find the area exactly? No. I'm just going to do, 1/2 times A times B times sine of C. And you have 1/2 times 23.04 times 37.06 times the sine of 44 degrees. And we do that, 0.5 times 23.04 times 37.06 times the sine of 44 degrees. We get 296.57 square feet. Now, if you do it exactly, you'll probably get something and see what we've got here. So, obviously, measure of angle A is going to be 99 degrees here. So, If I draw that, oh yeah, that'll be pretty good. And let's make this C as 4 miles. So here is angle C and here is angle B. Now, however, if you drew it differently from me, don't freak out, because here's why. Because the thing is, you're still going to have to set up the ratio for the law of sines. 19 over sine of 99 degrees equals B over sine of B equals 4 over sine of C. So it's pretty obvious all you're going to do here is figure out what angle C is, and we'll be able to figure out the area from that. All right, so you have 19 over sine of 99 degrees equaling 4 over sine of C. 19 times the sine of C will equal 4 times the sine of 99 degrees. If we divide that out by 19, you're going to be left with sine of C equal to a certain numerical value. Well, let's figure out what that is exactly. So we have 4 times sine of 99 degrees over 19. And that'll be 0.2079. So if we take the inverse sine of this, 0.2079, we're going to get, wow, something very close to that. It's just a real coincidence here. But what'll happen is this angle will be, wow, let's call it 12 degrees. Now, technically, it could also have been 168 degrees. But the reason we obviously can't go with 168 is why? That would make, 99 plus 168 is way, way, way above 180. So, yes. For angle, side, angle, well, no, this is angle, side, side. But, yeah, angle, side, angle could really just be, angle, angle, side, because if you know 2 angles, you know all 3 of them. But in that case, if you know 2 of the angles, you won't have the ambiguous case. Because what we're doing here is we're solving for an angle. So does that answer your question? All right, good. So, 168 is not going to fly for us. So we're going to treat this as a 12-degree angle. And, well, we can easily figure out what B is. And let's see, 180 minus 99 minus 12, that's 69 degrees. Now, we could figure out what side B is, but all I asked you to do is find the area. You could do 1/2 A times C times sine of B. Or you could use literally any ratio for that. 1/2 times 19 times 4 times sine of 69 degrees. And we get 35.5 square miles. That's a lot. That's a lot of square miles. All right, so that's going to be that. Now comes a applied version of it where we're going to get back to, you guessed it, bearings. So you're going to have two fire stations, call them A and B. B is going to be directly due east of station A. So it'll just be a horizontal line between A and B. And you're going to be able to figure out a fire spot C with the bearings. And what you can do is you can figure out how far to the nearest tenth of a mile is the fire from station B. So if you were to draw this, first thing you can do is draw a straight horizontal line. See, everyone's, when you ask them, like, what kind of a line is this? And they'll say straight. Well, all lines are straight. Here's A and B, and here's 18 miles. So 35 degrees east of north for A. So yeah, you go 35 degrees this way, but that also means that this angle here is what? What's that? Not supplementary, complementary. 90 degrees. So 35 plus what is 90? This is going to be a 55-degree angle. But you were on the right, you had the right idea. Now, 49 degrees west of the north line from B to C, yeah, that means we're going 49 degrees here. And that means this is 41 degrees. So basically, you're going to be finding this missing side length. You just need to find this distance here. Well, first off, we'll take 180 minus 45 minus, no, not 45, 55 minus, well, typos here, 41, and this angle is going to be 84 degrees. So we could just call this, little a. You have a over sine of 55 degrees equal to b over sine of 41 degrees, and it'll equal 18 over the sine of 84 degrees. So upon reading the question, they're just asking you how far to the nearest tenth of a mile is the fire, where C is the fire, from station B. So we're literally just going to be finding this side here. So you just do A over sine of 55 equals 18 over sine of 84 degrees. Cross multiply, A times the sine of 84 degrees equals 18 times your sine of 55 degrees. Divide out by sine of 84. And here's the thing, we're not going to get the ambiguous case here because we're finding a missing side. Now, if we were finding a missing angle, that's where we would be getting into the ambiguous case. So yeah, 18 times sine of 55 degrees. It's pretty cool. Over sine of 84 degrees.
Yeah.
Well, I'm going to multiply that by 1.0 and get 14.8 miles.
I was wondering why they calculated it.
Let me see here. Sine of 55. If I did 180 divided by 55, that's not an even fraction. I don't know why it did that. That's very interesting. But in the case that just happened with me, see, if I entered that on TI-84, just multiply it by 1.0, and it will get you what you need. I think it would have returned the same thing on a computer algebra system. Or maybe, I don't know why it did that, but let's just...
So like all those times where it trouble doing those massive fractions in the entire other thing that we did.
Yeah.
Now it gives us a fraction like that.
It gives you a fraction like that. I can't explain why.
But you can also go to math and just switch it over to decimal.
Yeah. Or, like what I do, and I tell a student that uses a computer algebra system, multiply it by 1.0, or like in statistics when we're calculating z-scores. How many of you have taken statistics? Yeah, like if we're finding 125 with a mean of 100 and a standard deviation of 35, it's going to give you a fraction. You'd have to make one of those a decimal in order for it to give you a decimal for the z-score. But so that's how you get around that. Now, to sum up your law of sines, we can solve a triangle in which one side and two angles are known, and the three known measurements can be abbreviated using side angle angle, or angle side angle, or in the case of side angle, that's going to be the ambiguous case. So basically, the ambiguous case can only result whenever you are given two sides and an angle that is not included between them. Now, what if we have other forms, such as all three sides? Well, here's the thing. All three sides, the law of sines is definitely not going to work for us. Now, the other possibility is side angle side, where the angle that we're given in this case is going to be in between the two sides. Now, here's an interesting question. What if I gave you three angles? Could you figure out the sides from three angles? Not definitively. Because I could have a triangle with three angles, but I could dilate it. I could multiply. Basically, it would be proportional. They can only be proportional. Three angles. See, I'll tell you that. So yeah, the branches of geometry. Let me ask you: in high school, when you took I know math was math 2 when you studied angle side angle congruences and all that. Yeah. Now, of course, that's all known. They don't really call it that in school, but it's known as Euclidean geometry. I had to take a course in non-Euclidean geometry, and it threw all those rules out the window. And it was like, what the heck? And I never really understood it. Probably because my teacher was terrible too. But we'll talk about that later. All right, so basically we have three versions of the law of cosines, where basically, you have a squared equals b squared plus c squared minus 2bc times cosine of a. And if you notice, the square of the side that is by itself here, in this case like b squared, what happens is you add the squares of the two other sides and subtract the product of twice the product of the other sides and the angle opposite that side. Now, basically what we're going to do is we're also going to be able to figure out a missing angle with these. Now, of course, with side, we have no way of figuring out angles using law of sines, so that's why we're going to use law of cosines. Now, with law of cosines, what we can do here is we could solve any one of these for cosine of A, cosine of B, or cosine of C. So that's how this is going to work. So, word of advice here, I would probably say figure out the largest of the angles first. So, in this case, we're obviously, we have all three sides. The law of sines is not going to work. So if we call this C, we call this A, and we call this B, here's the thing. We're going to figure out what angle C is going to be. Now, but here's the thing. You have C squared equal to A squared plus B squared minus 2AB times cosine of C. Now, if we want to figure out cosine of C, what we can do is we can literally solve that equation for cosine of C. So to do that, all we need to do, first thing we'll do is we'll subtract the A squared and B squared. But you'll probably be able to catch a pattern here very quickly. Equals negative 2AB cosine of C, and then we literally just divide out by negative 2AB. So what literally is going to happen here is we now have cosine of C equal to C squared minus A squared minus B squared over negative 2AB. Now, what we'll then do, basically plug in your sides and you're going to figure out cosine of C is going to equal something, and oh hell, just leave it as a fraction. That's going to make it even easier. So, cosine of C, that's going to be, let's see, not that. One day I'll get used to this. Let's see here. C is 26. So yeah, 26 squared minus 25 squared minus 20 squared over negative 2 times 25 times 20. Now, we get, wow, 349 out of 1,000. Or, yeah, cosine of C would be, 349 out of 1,000. So we literally take the inverse cosine. Now it's inverse cosine of 349 out of 1,000. Multiply that by 180 and divide it by pi. We get 69.6 degrees. Now, I would recommend finding out angle A. Now, in order to do that, the equation involving angle A is A squared equals B squared plus C squared minus 2BC cosine of A. And you have A squared minus B squared minus C squared, literally divided by negative 2BC equaling cosine of A. So here's the thing. Here's angle C, and notice there's no C on the bottom. The side C comes first. If it's angle A, no A is on the bottom, and A squared comes first. You could probably guess what cosine of B is going to equal to. So we plug and chug all this good stuff, and we can get, let's see what happens here. So in this case, A, so we'll have 25 squared minus 26 squared minus 20 squared over negative 2 times 26 times 20. And we get 451 out of 1,040. So if we take the inverse cosine of that ratio here, multiply that by 180 and divide it by pi, we get 64.3 degrees.
For argument's sake, once you have one of the angles, could you then just switch over to law of sines if you wanted to?
Yes. Great question. You could have switched over to law of sines if you'd wanted to. Now, if I wanted to find out measure of angle B, do I need to use law of cosines or sines? No. I just subtract it from 180. So we have 180 minus 69.6 minus 64.3, and we get 46.1, which we know is the smallest of the three sides. Now, here is an interesting little quirk you may or may not remember from Math 2 or geometry if you were in high school. Yeah. Basically, take the largest side and square it and compare it to the sums of the squares of the other two sides. Here's the thing. 26 squared is 676. And if we add 20 squared and 25 squared together, we get 1,025. Obviously, this is less. Now, since the largest side, the square of the largest side is smaller than the square, some of the squares of the other two, that makes the whole triangle acute. If the largest side squared, if the square of the largest side was larger than the sum of the squares of the other two sides, it would be obtuse. Now, what if that ratio is equal? What kind of a triangle would that be? It would be right. A right triangle. So, and what we could have done here to figure out angle A was use the law of sines. Now, problem is, the law of sines, in a way, would open up to an ambiguous case, but it really wouldn't. Because if you figure out the largest angle first, yeah, the other angle could have been something in change. Yeah, it wouldn't have worked.
Well, say it is a right triangle, which means you already have your 90-degree for one of your angles. Which side does that goes adjacent to the largest side, correct?
Yes. Well, if they were equal, then basically you could just use any ordinary trig ratio. But that's just a little thing to remember from back in the day. All right, now I want you to find all the missing information for this triangle. Now, before we go off on our own and do this, you'd have 16 over sine of A equal to 21 over sine of B equal to C over sine of 126 degrees. We cannot use law of sines in any way here. Now, one thing, you could find this missing side by using law of cosines, and then you could use law of sines or law of cosines. I mean, here's the thing: if you use law of sines after that, there is no room for the ambiguous case because that's already an obtuse angle. So I would go about finding side C. All right, so if we set up the law of cosines, you have c squared equals a squared, oh, come on, plus b squared minus 2 times a times b times cosine of c. So, yeah, here's b and here's a. I mean, it really doesn't make much of a difference. But yeah, 16 squared plus 21 squared minus 2 times 16 times 21 times cosine of 126 degrees. And chances are you're going to get a decimal for this. 16 squared plus 21 squared minus 2 times 16 times 21 times cosine of 126 degrees. We get c squared equal to, I would just round that to 2 decimal places, 1091.99. I mean, if you rounded that to 1092, I probably wouldn't freak out too much. But yeah, 1091.99, square root of that, that's going to be 33.05 kilometers. Now, obviously, side C is largest. Now, what we could do here is we could figure out the measure of angle B using either law of sines or law of cosines. I'm going to do it both ways just once and show you, hey, it works. So here's the thing. 21 over sine of B will equal 33.05 over sine of 126 degrees. So sine of B is going to be 21 times sine of 126 degrees over 33.05. And we get 0.5141. We'll take the inverse sine of 0.5141. And we get this, multiplying that by 180 over pi. And we get 30.94 degrees. Now, let's just call it 30.9 degrees. Now, the other possibility would be 180 less that, but here's the thing. It's not even going to happen because you'd have two obtuse angles, which probably would work in non-Euclidean geometry. See, all the rules for Euclidean geometry go right out the window. And I think that's one of the reasons I hated non-Euclidean. Like, when are we ever going to use this? I mean, that's a terrible thing for a teacher to say, but yeah. Now, even though we already did this, I'm going to do cosine of B. That's b squared minus a squared minus c squared over negative 2ac. So, let's see here. B was...
One of those lines would have to curve.
Exactly, and it is. That's why...
Oh, then you have to put that curve.
That's why I truly never understood it. And that was just the one thing I never got. And I mean, I could think of something from every other class that I took in graduate school that has applied here. So 0.8579, if I take the inverse cosine of 0.8579, I get this, multiply it by 180 and divide it by pi, I get 30.9 degrees that way. Of course, they're going to be a little bit different because of rounding, but Yeah, see, it all works. And of course, yeah, 30.9 degrees. Angle A, you could use a trig ratio if you wanted, but no, we've done enough of that. 30.9, and we get 23.1 degrees. All right, easy enough, see? Easy come, easy go. Now, I want you to find the missing information for this coming triangle right here. All right, let's call this little a, let's call this little c, let's call this little b. So you have a squared equal to b squared plus c squared minus 2bc times cosine of 106 degrees. So it's 10 squared plus, what's that, 17 minus 2 times 10 times 17 times cosine of 106 degrees. And 482.72. But we have to take the square root of that. 482.72, we take the square root, and we get A equal to 21.97 inches. I don't know what my lab exactly calls for rounding, but I mean, yeah, if I said 1 decimal, A equal to 22 would be good, but 2 decimals is kind of my little rule of thumb here. Now, I could use either law of sines or law of cosines to figure out angle C, or for that matter, angle B. I always kind of have a little rule of thumb. If you have the largest angle, go for the next angle. So, in other words, you have 21.97 over sine of 106 degrees equal to 10 over sine of B, but let's just make it 17 over sine of C. So, yeah, anytime you use law of sines to find an angle, there are 2 possibilities, but when one of the angles is already acute, then it's not going to be the ambiguous case. Now, of course, if you want to avoid the ambiguous case, you could use law of cosines to find out what angle C is. But we already got this party started, so let's finish it. So, yeah, 21.97 times the sine of C equals 17 times the sine of 106. Divide that by 21.97. And let's see what we get here. 17 times the sine of 106 degrees. Over top of 21.97. And 0.7438, we take the inverse sine of 0.7438 and multiply that by 180 and divide it by pi. We've got measure of angle C equal to 48.06 degrees. And basically, it could have also been 180 less that, which would have resulted in an obtuse, but no need for that. 180 minus 106 minus 48.06. We get 25.94 for the missing angle, and that's it, my friends. side here of 21.97 inches. Now what I want you to do is to find the area, even though I didn't specifically say so. I want you to find the area for this particular triangle, please. I'm going to show you is basically use the area equal to 1/2 times b times c times the sine of a. Now we could have done, a 1/2 times a times b times the sine of c. We could have done it that way too. So you have 1/2 times 10 times 17 times the sine of 106 degrees. So we use our calculator to figure out what that's going to be. 0.5 times 10 times 17 times sine of 106 degrees. And we get 81.71 square inches. Now, if we had done, different version, we would have gotten the area the same way. But we have another formula to figure out the area of a triangle, especially when we're given all three sides, and that is going to be known as herons, or you might see it as heroes, kind of a more anglicized version of it. But Heron's formula basically just takes the side lengths into account, where first thing you'd have to do is you would have to figure out what S is, and S is literally 1/2 of the perimeter, 1/2 times A plus B plus C, or some might call it the given, or the semi-perimeter. But either way, we have all three sides, so the first thing you'd have to do is figure out what S is. If A is going to be 21.97, B is going to be 10, and C is going to be 17 inches. What you're going to do is, first thing you'll do is we'll figure out what S is. So to figure out S, you take the 21.97 plus 10 plus 17, and we're probably going to get a decimal here, but that's okay. And it's going to be 24.485 inches. Now, because remember, S is still going to be in inches because it's the perimeter. You literally just add the lengths of the sides together. That's all you have to do. Now you basically get to punch this into your calculator just like so. And I'm also going to kind of just show you, 24.485 inches times 24.485 minus 21.97 inches. You don't have, what I'm going to do here is more or less show you how the area is still going to come out to be square inches. In other words, you are not going to need to put the individual inches inside of here. So you have 10 minus 24.485 inches, and then 17 minus 24.485 inches. So basically, you could just do it in one shot on the calculator here, but what'll happen is you have the square root of inches to the fourth. Now, what is the square root of something squared? Something to the fourth. I just gave the answer away. It's going to be in inches squared. There really should be no such thing as like quartic inches. But yeah, that's what we got here. So basically, all you really need to do is just kind of plug this in, 24.485 times 24.485 minus 21.97. And one thing you could do is, if you really want, you could actually store the S as a variable and just type it in. Oh, it's the other way around, but it's really not going to make a difference.
It was S minus.
It is S minus that. Oh yeah, it is.
That's why when you write it down.
Oh, duh.
I'm confused. That's going to give us negatives in those values.
I don't know why I wrote it like that, but yeah, it should have been S minus 10 and then S minus 17. Yeah, I don't know what I was thinking here. Okay, so 24.485 minus 17, we close all that off, and we get 81.71 square inches, which is roughly what we got for law of sines version. Now, again, if you're calculator savvy, you could store that S, or I mean, you could easily store it as X and do the calculations kind of that way if you really wanted. But, you know, that's what you're going to get. All right, so with that in mind, I want you to find the missing angles as well as the area for this. Here, so let's figure out, so yeah, this is C, this is A, and this is little b. Now, if you remember from your law of cosines, which, by the way, I'm going to give you law of sines and cosines on the test. But here's the thing, I'm not going to give you the version that's solved for the angle here. So basically, you have c squared minus a squared minus b squared over negative 2ab equal to cosine of c. Now, if you wanted, you could divide everything out by a negative and get rid of the negative sign on the bottom, but just please do it like this. I think it would be just as easy. All right, so you'd have 17 squared minus 11 squared minus 10 squared over negative 2 times 11 times 10. And let's see what that is going to equal. And we get negative 17 over 55 for cosine of c here. Now, if we take the inverse cosine of negative 17 over 55, that's going to give us a second quadrant angle, which in reality is actually a good thing. And this is going to be 108 degrees. Now, we know that, yeah, if we wanted to find the law, so if we wanted to go about finding B or A, if we used law of cosines, we wouldn't have to worry about an ambiguous case. And if we went about it with the law of sines, there is the possibility, but here's the other thing. Like whatever we get for B, like, I don't know, let's figure out what B is using law of sines. So let's see here. You have 10 over sine of A equal to 11 over sine of B equal to 17 over sine of 108 degrees. So basically 11 times the sine of 108 will equal 17 times your sine of B, dividing up by 17 here. Sine of B is going to equal this whole mess. So we figure out what it's going to be. So that's going to be 11 times the sine of 108 degrees over 17. And therefore, sine of B is going to be 0.6154. Now, when we take the inverse sine of this, 0.6154, and convert that to, because I keep my calculator in radian mode perpetually, and that's going to be 37.98 degrees. But it could have also been technically 180 minus that. But here's the thing. That is a very obtuse angle, and we already have one obtuse angle. So basically, we can just forget about the other one. Now, you could have also used law of cosines to figure out the measure of angle B if you really wanted. And you could use law of cosines to figure out the measure of angle A. But wait a second. We have two angles. Why bother with law of sines or cosines? Just do it this way. And we get 34.02 degrees. Now, find. All right, so if I wanted to figure out the area, I'm just going to use Heron, or Hero. So you take 1/2 times 17 plus 11 plus 10, and that's going to be your value of S. And we get 19. And these are all in kilometers. So you have 19 times 19 minus 17, 19 minus 11, and 19 minus 10. So you can just take the square root of 19 times 2 times 8 times 9, and we get 52.31 squared kilometers. Yes. So should we get the same thing? Yes. The answer is definitely yes. So why not do it? Is it going to break our leg? No. So I could use, let's see, 1/2 times 10 times 11 times the sine of 108. Let's see what I get for that. Excuse me. Yeah, get the same thing. Pretty neat. All right, I'm going to have you try. All right, so yeah, c squared is going to be, this is going to be A, this is going to be B. So let's see here, 24 squared plus 22 squared minus 2 times 24 times 22 times cosine of 106 degrees. Minus 2 times 22. A lot of 2's in here. Cosine of 106 degrees. And then you can take the square root. One thing you can do is, if you want, you can draw square root and do this. And C is going to be 36.76 yards. But if you gave me 36.75, I'm not going to freak out too much. So that's what we get for this one. C is going to be 36.76 yard. And we need to figure out one of the missing angles here. So let's go ahead and figure out what angle A is. So you'd have 24 over sine of A equal to 22 over sine of B equal to 36.76 over sine of C. Now, of course, again, you could have used law of cosines to find out what angle A is. But a lot of you probably like law of sines a little better. I kind of like law of cosines myself. Oh, sine of 106 degrees. So 24 times the sine of 106 divided by 36.76. That's what sine of A will equal. And let's see what that is exactly. 24 times the sine of 106 degrees over 36.76 and 0.6276. So take the inverse sine of that. Times 180 over pi. As usual, 38.87 degrees. And then 180 minus 106 minus 38.87, 35.13 degrees. So you can figure out the area using any rule you want, whether you use a sine version or Herons. I'm gonna go with Herons again because, well, why not? So 24 plus 22 plus 36.76. And we get 41.38. So the area is going to be, 41.38 times 41.38 minus 24. 41.38 minus 22. And 41.38 minus 36.76. Now, what I was talking about a little earlier was, let's say I store that to x. And I could just do x times x minus 24 times x minus 22 times x minus 36.76. Now, do you really need those multiplications in there? No, not really. But the area is going to be 253.76 square yards. Now, if you did this with one of the sine ratios, such as, 1/2 times 22 times 24 times sine of 106 degrees, I kind of just did that up here. Yeah, I get, well, a little bit different, but there you have it.
That's close to what I got whenever I stored C's sine
Yes.
value as X, and so and put the entire thing in.
So here's the thing.
Be like S minus X.
We could have stored 36 points. We could have stored C as the actual side length of 36.76, blah, 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 and change. Figure out S from there, and it would give you the exact value. So,
yeah, I got exactly that.
Yeah, if we actually went ahead and figured out what that C was again.
It's just a lot of extra work. You got to do double storage.
Yeah, it's double storage, but it's not the end of the world. Oh, yeah, here we go. So, yeah, if I stored that to, say, C, 0.5 times, what are the sides? 22, 24, and C. And I could store that to S, or you know what? I'm going to go ahead and store it to S. So basically, if we do the S times S minus 24, see, this is when doing it on an Inspire is so much better. Yeah, that's what I love.
That's what I meant by like the double storage for
Yeah.
a little rough, because it's like old school texting where you got to tap the numbers a couple times to get your letters.
But if you look at this 253.77, that is the more precise, that is like the most precise one. In fact, it is exact, So as I want to again point out, you will get something very, not exactly close, but close enough for our sake. All right, skip this next one. I want you to figure out a bearing question. So here we go. So yeah, here's the airport. We'll call it that. First plane is going to fly 400 miles per hour due north. So after 3 hours, how far has that plane traveled? Yeah, that plane has traveled 1,200 miles. And this is a terrible drawing of a plane, but yeah. Now we're going to go 75 degrees east of the north line. And at 350 miles an hour, so this one's going just a little bit slower. What is the speed? How far has the plane traveled here? 1,050 miles. And here is plane B. So this is a 75-degree angle. So what you can do here is basically figure out how far apart they are. All I really have to do here, if we called this, x, it's literally just going to be x squared equals 1,200 squared plus 1,050 squared minus 2 times 1,200 times 1050 times cosine of 75 degrees. So let's see what we get for that. And we get this giant thing. So we take the square root, and we get, let's just round it to the nearest mile. X is going to be 1,375 miles apart. All right, not bad. All right, so why don't you do the one before this? So I'll tell you what's going to happen tomorrow. The square of the largest side is less than the squares of the smaller two sides. That's what makes this an acute triangle. Of course, we were able to figure out that it was an acute triangle from the get-go. All right, so tomorrow we have you. So the foundation of our polar coordinate system is a horizontal ray that extends to the right, and that's going to be called the polar axis, as you see here, not the polar express. Gee, that would be kind of It would be cool if we did this a little closer to Christmas, but no. The endpoint of the ray is going to be called the pole here, and a point P in the polar coordinate system is represented by an order pair of numbers r theta, and you can probably guess r is going to be the radius and theta is going to be the angle. Now, the formal definition of r really is the directed distance from the pole to P. And theta is going to be your angle from the polar axis to the line segment from the pole to P. And you can measure that in degrees or radians. So positive angles are measured counterclockwise, negative angles are measured clockwise. Of course, we kind of know that. And effectively, yeah, this is a unit circle if we only had a radius of 1. But this unit circle goes on to a distance of 4 here. But we're going to spend most of today plotting polar points and converting them to rectangular and coming up with other representations. So here's an easy scenario here. If we were asked to plot the point 2 and 330 degrees. Now, problem is on this polar paper, on this polar graph, you don't see the angles in degrees. So 330 degrees times pi over 180. Let's see here. Yeah, so 330 divided by 180, or basically 33 over 18. I mean, yeah, and the amount of time that I'm taking to enter this here, this is 11 pi over 6. So this is the same thing as saying 2 and 11 pi over 6. So this would be your point right here. Plain and simple. Now, we can also do other representations of this, but let's just get some basics out of the way first. If you were to plot the point -3 and pi over 2, I'll let you value, or the radius value, you typically go in a positive direction here. But since it's negative, you go in the negative direction. The angle is going to be pi over 2. But since you're going in the negative direction, it's going to land right here. Now, come on. Let's see here. Okay. So how could we represent this as, in another form? Well, you could also represent this as, say, maybe 3 and 3 pi over 2. But yeah, so you understand here, the pi over 2, but instead of going to positive 3, you do -3, you go in the opposite direction. So that's how that's going to work. All right, so with that in mind, let's look here. Plot this and come up with some other representations. So here's the thing. If we do -2 pi over 3, so here's -1 pi over 3, -2 pi over 3, but we want to do -2 there. So here's the thing. This is +2 with that. So the -2 would take us to here at this location. So what would be another representation of this? Well, you could have just simply called it -2 and 4 pi over 3. But what about where the r is positive? How could you write that with a positive r? Well, let's see here. Positive 2 pi over 3 puts us here. So not quite, but what would the angle be if it was a positive 2 for the r? Pi over 3. Now, one thing we're going to be able to do here in a little while is convert these. So let's just worry about, how can we convert these? Well, that's actually easy here. If we wanted to convert between polar and rectangular, rectangular is the standard system that we have been doing for years. Well, not for years really, but for a much longer time span here. So what'll happen is I'm going to give you a polar point, and you can just do r cosine of theta and r sine of theta, and you can get the x and the y coordinate. Now, this is also going to be helpful when we're going to convert rectangular, that's xy, to polar. We're also going to be doing the same thing for converting equations. And we're going to show you how to graph polar equations in the calculator. It's actually not too bad. So we're going to focus right now on simply converting polar to rectangular. So if I wanted you to have here's the polar coordinate, 4 and 3 pi over 4. Now, one thing I'm still trying to find, and I have a lot of trouble doing so, is trying to find a graph paper that has both, polar and rectangular on it. So this is going to be rectangular graph paper here, but we should be able to see it. So in order to convert this, now 4 and 3 pi over 4, what quadrant would you end up in? The second quadrant. So x is going to be, r is 4, and theta is simply 3 pi over 4. So it's going to be 4 times cosine of 3 pi over 4. And y will be 4 times the sine of 3 pi over 4. Now, you will have to give me the exact values, but you also have a unit circle in front of you. I'm not going to give you like pi over 12 or anything that kind of absurd because, well, frankly, we just don't have the time for it. So, cosine of 3 pi over 4 equals what? Negative root 2 over 2. So 4 divided by 2, that's going to be a 2. So it's just going to be negative 2 root 2. And for the y coordinate, the sine of 3 pi over 4, it is positive 2 root 2, or positive root 2 over 2, and that'll become simply 2 root 2. So the rectangular is simply going to be negative 2 root 2 and positive 2 root 2. Now, as I said, I want to know what these coordinates are in exact form. And by exact form, I mean radicals. But let's get the decimal equivalences to these real quick just to kind of plot it. Negative 2 root 2 is going to be negative 2.82, so right about here, and positive 2.82 is going to put us right about here. So it's simply going to look like this. Probably not the best looking graph here, but yeah, this looks definitely like 3 pi over 4. Now, if you actually do negative 2 root 2 quantity squared plus 2 root 2 squared, that's going to be, what's that going to equal? Well, the negative 2 root 2 squaring, that gives you 8. Positive 2 root 2 squaring, that gets you another 8. So this adds up to 16. And 16 is equal to r squared, so r equals 4. So the little hint here is when I give you a rectangular coordinate, you'll be able to find the r value very simple. And again, I am still trying to find, imagine concentric circles being placed here. I should just try to draw one in some way. I'm going to do it one day. But what I want you to do is figure out the rectangular coordinates for this representation. All right, so x is going to be 2 times cosine of negative 5 pi over 6. And y is going to be 2 times the sine of negative 5 pi over 6. So even though that's a positive 2, negative 5 pi over 6 puts us here in the third quadrant. So if we take the cosine of negative 5 pi over 6, that's going to be negative root 3 over 2. And that's simply going to wind up with square root of 3. And the sine of negative 5 pi over 6 is going to equal negative 1/2, which is negative 1. So basically, your rectangular coordinate is simply negative root 3 and negative 1. And that's going to put us right about here, because negative, root 3 is 1.7 and change. And again, if we drew like a concentric circle, it would be where that radius of 2 is, plain and simple. Okay, so first off, that's a positive radius, but the angle is negative 5 pi over 6. So you go clockwise. No, because, excuse me, because negative 5 pi over 6, here's negative 6 pi over 6, here's negative 5 pi over 6. But when you find the cosine of negative 5 pi over 6, you get this. And the sine of negative 5 pi over 6, you get that. You multiply them out, and both the x and the y coordinates are negative. So that's how it's going to work. Well, here's something you could do. Negative 5 pi over 6, you could have done positive 7 pi over 6. I mean, if you did the cosine of... So what we're saying here is that this polar representation could also be represented by 2 with positive 7 pi over 6, because you added 2 pi to get to that. And if you do the cosine of 7 pi over 6, you're going to get negative root 3 over 2. This is where, sometimes I really wish this calculator would give it to you in exact form. But that is negative root 3 over 2. I recognize that because I've been doing this for so long. But yeah. All right. I want you to try this one. Look at this one. Negative 3 and negative 5 pi over 3. So basically, if I wanted to go negative 5 pi over 3, I could, go this way and then negative 3. So that's going to put me into the third quadrant from what I'm seeing here, but that's okay. But I could also re-represent this as something else. I could do negative 3 and positive pi over 3. Or one thing I could do, here's positive pi over 3, but if I'm going negative 3, I go in this direction here, so it's going to end up somewhere here. So you know what? It's probably easier to just leave it like that. But x would be negative 3 times cosine of pi over 3. And the cosine of pi over 3, see, by now you would think I would have these memorized, but I don't. But cosine of pi over 3, that's going to be 1/2. So you have negative 3 times 1/2, or negative 3/2. And the y value is going to be negative 3 sine of pi over 3. Well, that's going to be negative 3 times root 3 over 2. So that's going to be negative 3 root 3 over 2. So, but if you had done, negative 5 pi over 3, long story short, this is the representation, negative 3/2 and negative 3 root 3 over 2. Now, 3/2, that's of course negative 1.5, we know that. Negative 3 root 3 divided by 2, that's negative 2.6. So that's going to put somewhere right around here. And I connect that. So if I went, negative 5 pi over 3, which is like all the way around here, and then negative 3, see, it's right there. All right, so now we get to have some more fun with this by converting from rectangular to polar form. And again, one day, I keep saying this, and I never find it, because I guess maybe I get sidetracked or something too easily. But I try to find, I want to find like graph and polar and rectangular paper. I should just kind of Google it, like rectangular graph paper with circles, see if I can find that. But first thing you could do is plot the point, kind of get an approximation, and you'll find out what r is, and then you'll find out what theta is. Now, here's the thing. Tangent of theta is y over x, so you could take the inverse tangent of theta, but be mindful of the quadrant. Or, because you're finding out what the r is, you could actually use an inverse sine ratio or an inverse cosine ratio. So I'm going to walk us through this one here. The first thing we need to do is we need to figure out what the r is. Well, the r is actually going to be relatively easy to do here, because we actually saw whether these are positive or negative, when we square them, when we square negative, it becomes a positive. So you have 3 root 3 over 2 squared plus 3/2 squared. Now, you can enter that in one shot on your calculator, and any one of these I ever give you will have an r value that is a perfect square. In other words, you're not going to have to simplify some extra radical here. So, you can do this on your calculator. Let's see, that's 9 times 3 over 4 plus 9 over 4, and that's 36 over 4, which is 9. Now, by the way, that's r squared, I'm sorry. So r is going to be 3. Now, I'd said, oh, that's easy because, see, we had negative versions of this, but the r is going to be a 3. Now, when we figure out the angle, the nice thing about this is, what quadrant is this going to put us in? It's going to put us right in the first quadrant here. So one thing we can do here is basically just do, tangent of theta equal to y over x, which is literally 3/2 over 3 root 3 over 2. The 2's kind of cancel, and you're left with 3 over 3 root 3, which is 1 over root 3. And basically, you could take the inverse tangent of 1 over root 3, which does become square root of 3 over 3. And now, if your calculator was in degree mode, you would recognize this as a 30-degree angle. So theta is going to be pi over 6. So pi over 6 or 30 degrees, it's going to put us, let's see here, 1, 2, 3, right here. Yeah, I'll draw that one in blue here. Wait, yeah. And yeah. So yeah, 3/2, if you actually plot that, yeah, the vertical distance appears to be 3/2. Now, here's another thing you could have done if you really wanted. One other thing you could have done here is, obviously, wrong place. You could have made this a 3, and this would have been 3/2. And if you wanted to find theta this way, you could do sine of theta equal to 3/2 over 3, or where the sine of theta is going to equal 1/2. Well, where is the sine of theta equal to 1/2? At pi over 6. So you could have done it that way too. But it's not going to be always this cut and dry, especially when we get into other ones that are outside of the first quadrant. So what we want to do here is keep that theta between 0 and 2 pi. Because what's going to happen is, if you took the inverse tangent of that setup, you'll probably get an angle that is not between 0 and 2 pi. But I want you to give me the theta between those two angles. And for the lab, yeah, rectangular to polar, yeah, on the lab I wasn't specific, so technically if you give me any angle, I can't mark you wrong as long as it works. But yeah, I do want to be specific here. Like when it comes to your test, I'm going to be specific. So let's see here. So first off, r squared is going to be 2 squared plus negative 2 root 3 quantity squared. Well, that's 4 plus 12, that's 16. So r is going to equal 4. Now, for the theta, you could just do, tangent of theta equal to negative 2 root 3 over 2 here, or negative root 3, and you can take the inverse tangent of that. If you take the inverse tangent of negative root 3, what's that going to do here? Well, that gives you a negative angle here. That's going to be negative pi over 3. But here's the thing. This point itself would be in what quadrant? That would be in the 4th quadrant. Now, negative pi over 3 actually does put you in the 4th quadrant, but I'd rather have the angle be positive, so you could add 2 pi and get 5 pi over 3. So the polar form is just going to be 4 and 5 pi over 3. So 5 pi over 3, or 300 degrees. Let's see here. We have 1, 2, 3, 4. And if we were to draw this kind of as a little kind of a box thing here, you can see the horizontal distance is in fact 2. And the vertical distance, negative 2 root 3. Negative 2 root 3 is roughly what? It's going to be like 3.4. Well, there it is. All right, try that one. All right, so the first thing we'll do is we'll figure out what r is. All right, so yeah, r squared is going to be negative 3 squared plus negative 3 root 3 quantity squared. Let's see, that's going to be 9, and that'll be 27 for 36. So r squared is 36, so r is simply going to be 6. Now, both of these are negative, so that's going to actually put you into what quadrant? That's going to put you into the third quadrant. Now, one thing that's going to happen here, though, is if we actually took, tangent of theta equal to negative 3 root 3 over negative 3, and that's simply going to be square root of 3. If you took the inverse tangent of square root of 3, that's going to give you the first quadrant angle. So this is why I say you have to check, the quadrant. That's obviously going to be pi over 3. If you're not sure that that's in fact pi over 3, there it is. So again, we get theta equal to pi over 3 from this, but that's, again, not the angle that we're going to be working with here. What we're going to be working with, let's see here, keep this in mind. This is third quadrant here. So pi over 3 or 60 degrees, but it's here. So basically, that's going to be the theta that we really want is going to be 4 pi over 3. Now, here's the thing. If you actually took the not inverse tangent, but the tangent of 4 pi over 3, you would get the square root of 3 from that. So that's one thing you would get. So basically, it's going to be 6 and 4 pi over 3. 4 pi over 3, that's what, 240 degrees. So you have 1, 2, 3, 4, 5, 6 right here. All right. Any other questions on this? All right. So what we're going to do here on the next page, and I'm going to throw, let me just double check that it is in fact page 20. Yes. Page 20 shows how to graph polar. polar equations. So instead of x and y, a polar equation is going to have r and theta in it. So all we got to do is simply replace any x's with r cosine of theta and y's with r sine of theta, and you'll end up solving it for r. Now, we're going to do linear ones first. Now, 3x minus y equals 6. That's obviously a linear equation. So how do you graph a polar equation? Well, here's the thing. If you go to mode, and instead, for function, we're going to do parametric towards the end of the course, but we're going to switch this to polar. And when we go to y equals, it's going to be r. You'll see like r1, r2, and so on. And so I'll set up the fraction here. This will be 6 over 3 cosine. Now, here's the thing. When you push this button, that button, in addition to x, it says t, which is used for parametric, theta, which is used for polar. So, and n is for sequential. We don't touch that. So then we graph it, and that looks like a linear equation. Well, it doesn't look like one. It is. In fact, yeah, 3x minus y equals 6. If I solve that for y here, y would equal positive 3x minus 6. And if you notice, yeah, go up 3 over 1. So I think this will be the last thing we do here, is we're going to convert that to polar form. So what will happen is you'll replace the x with r cosine of theta, and you'll replace the y with r sine of theta, equal to 9. Now, I could multiply out all of this and get 5r cosine theta minus 3r sine of theta equal to 9. Now, what we did here, and what you'll ultimately need to do, is factor an r out. So if I factor this r out, it's going to be r times 5 cosine of theta minus 3 sine of theta equal to 9. And then the last thing we do is we divide out by everything that's not r. 5 cosine theta minus 3 sine theta. And you have r equal to 9 over 5 cosine theta minus 3 sine theta. And that's it. All right, this is where we left off last time. So, and again, if you look on page 20 in these note packets, what you'll see is it'll explain how to graph a polar equation. So what we got here now, if we switch it to polar mode, and you'll have 9 over 5 cosine theta minus 3 sine of theta, and we see that that's definitely going to be a line here. Well, 5x minus 3y equals 9. That is a line. Now, this one is going to be a little bit more interesting. If we had y equals 2x, now, thing is, we know that y equals 2x is a linear line. Well, all lines are linear. It's going to be a linear equation, and it'll pass through the origin. So we don't have anything pertaining to r here as it's written here, because see, here's the thing. Y gets replaced with r sine of theta, and x will be replaced with r cosine of theta. Now, what will happen here, though, is when we divide both sides of this by r, we're going to end up with no r in this. Sine of theta will equal 2 cosine of theta. And if we divide by cosine of theta on both sides, we basically get tangent of theta equals 2. So what's going to happen here is very simple. You're going to figure out what theta is for this. And, unfortunately, this is not going to be on the unit circle or anything like that. So what you would do here is basically take the inverse tangent of 2. Oh, I want to switch back. Oh, yeah, I'm going to switch it back to function mode. And if I do the inverse tangent of 2, here's the thing. That's going to be as an angle, multiplied by 180 over pi, and we get theta equal to about 63.43 degrees. So 63.43 kind of puts us right about here, and it will definitely go through the origin. And you can more or less tell, yeah, y equals 2x, it's going to look like this. So that's what we're going to get for this. Now, let's look at the next one where, yeah, you convert that to polar form. This time you'll get an angle that is on the unit circle. Do that. Okay, so anyway, yeah, you did this. I explained it. So this is an equation of a circle. Now, we're going to convert equations of circles and even parabolas into polar form. So what happens is you simply replace your x's with r cosine of theta and your y's with r sine of theta. And, r cosine of theta squared is r squared cosine squared theta. Expanding this, r sine theta plus 3 quantity squared. You FOIL that out, you get r squared sine squared theta plus 6r sine theta plus 9 equaling 9. And you could take an r squared out of the first one, out of the first two, because here's the thing. Cosine squared theta plus sine squared of theta is going to equal 1. And basically, we factor an r out of this, and you get r equal to 0 or r equal to, or r plus 6 sine of theta equal to 0. And solving that for r, you get negative 6 sine of theta. Now, let's go to graph this. So yeah, we're going to go back into polar mode. And this time, yeah, negative 6 sine of theta. And that will be a circle. Even though it looks like an ellipse, it does kind of look like an ellipse here. And the reason it does is because of the distortion on our calculator. So that's what that's going to look like. Now, what I want you to do is for this next one, I want you to convert that to polar form. Again, the radius for this one will not be an integer, same with the next one. But there is a reason why it's going to be a 5 on that side, because if it wasn't, life would be much more complicated. That made me happy. All right, so if you remember, x is going to be r cosine of theta, y is going to be r sine of theta. So you have r cosine of theta minus 1 quantity squared plus r sine of theta minus 2 quantity squared equaling 5. Yeah, what's going to happen is on the left-hand side, you're going to end up having it equal to 5 entirely. Well, yeah, after you do all of your work, it's going to equal 5. So r cosine of theta minus 1 times itself. So for the first part here, yeah, you have r squared cosine squared theta, and you can write out the minus 1r cosine theta minus 1r cosine theta, or you could just say minus 2r cosine theta, and negative 1 times itself is going to be positive 1. And then for the sine, you have r squared sine squared theta minus 4r sine theta plus 4 equal to 5. Now, one of the things I talked about was, yeah, the left-hand side is going to equal 5 here. So basically, you can eliminate the 5, so to speak, and you still have to do a little bit of manipulation here, but it's always going to work out this way. In other words, 1 plus 4 would be 5. So like you could have a 1 plus a 9, and the other side would equal 10. So basically you have r squared cosine squared theta plus r squared sine squared theta minus 2r cosine theta minus 4r sine theta equals nothing. Well, you have r squared times cosine squared theta plus sine squared theta minus 2r cosine theta minus 4r sine theta equals 0. And so that just becomes a 1. So yeah, r squared minus 2r cosine theta minus 4r sine theta equals 0. So what we then can do is factor an r out of the left-hand side. So to do that, take an r out here, and that'll be r minus 2 cosine theta minus 4 sine theta equals 0. So basically you have r equals 0, or r minus 2 cosine theta minus 4 sine theta equals 0. So you can solve that other one for r by adding both of these. You have r equals 2 cosine theta plus 4 sine theta. Now, how can you verify that that's right? Well, that's actually very easy to do. All you got to do is graph that. Now, keep in mind, the original equation is still a circle that's centered at where? What are the coordinates of the center for this circle? That's what I'm talking about. What's the center for that? It's going to be 1, 2. And the radius is going to be the square root of 5. So as I said, the radius for a lot of these will probably not be an integer. That's okay. So what we're going to do here is, if we go to graph this, 2 cosine theta plus 4 sine of theta. And we see it's definitely centered at 1, 2. All right, I want you to try this next one for me. All right, so this is going to be a circle that is centered at where? 3, -1, and the radius is going to be the square root of 10, which is a little more than 3. So, when you do these, the thing is, you're going to see, it's almost like a pattern to this. You have r cosine theta minus 3 quantity squared plus r sine theta plus 1 quantity squared equals 10. And, when you go to FOIL it out and everything, this would be r squared cosine squared theta minus 6r cosine theta plus 9 plus r squared sine squared theta plus 2r sine theta plus 1, that's going to equal 10. And as I said, 9 and 1 would add to 10 here. So if I move this out here, basically you have r squared cosine squared theta plus r squared sine squared theta. In other words, this is always going to be a plus here, by the way. That will never be a minus. Minus 6r cosine theta plus 2r sine theta equaling 0. Well, if I factor the r squared out of cosine squared theta plus sine squared theta, cosine squared plus sine squared theta simply adds up to 1. So you can just call this r squared minus 6r cosine theta plus 2r sine of theta equaling 0. Factor an r out. So we've got r equal to 0, really nothing doing with that. R minus 6 cosine theta plus 2 sine theta equals 0, or r will equal 6 cosine theta minus 2 sine theta. Now, what you can do is you can graph that polar equation, and let's see what happens. 6 cosine theta minus 2 sine of theta, and 3 -1. And again, that looks kind of ovalish, but it's really not. In fact, if you hit zoom 5 for a zoom square, and even though it's not going to be a 10 by 10, it's going to be a little more realistic looking. All right, not bad. Now, convert that one to polar form. I'm going to see what you can do with that. But what we're going to do here is we're going to see what the polar form of this bad boy is going to be. So you have r sine of theta equal to r cosine of theta quantity squared. So you've got r sine of theta equaling r squared cosine squared theta. Now, this one will be solvable for an r. Now, one thing you can do, though, is you can divide both sides by r right off the bat, and you'd have sine of theta equal to r cosine squared theta. Now, if you were to want to solve this for r, well, that's very easy. All you have to do is divide both sides by cosine squared theta. Now, I wouldn't give this one to you on a test here, because here's the thing. I wouldn't like my answer like this. And see, what they would say is, write this without a fraction. Well, it is very possible to do that, but here's what happens. If we go to this, and we actually do sine of theta over cosine of theta squared. That's a parabola, if I ever saw it. But if I took out, imagine that I took out split this bottom up here. Times 1 over cosine of theta. Sine over cosine, well, that's tangent. And 1 over cosine is secant. So you theoretically could do tangent of theta times 1 over cosine of theta. Or if you had to inspire, you could do secant. But your calculator doesn't do secant. See, that's the answer I would want if I were giving this to you on a test, but I wouldn't. So you're kind of good in that sense. All right, let's see here. Now, in addition to polar conversions, we can also convert from polar to rectangular form. Now, let's look at r equals 4 first. Now, if you actually were to go in and graph r equals 4, see, that's a circle. Yeah, it's a circle with a radius of 4. So basically, you have r equals 4. Now, if you squared both sides, you would literally have x squared plus y squared equals 16. So basically, you can replace, you can do a little bit of math here and figure some things out. Now, tangent of theta, equaling 4. What is that in rectangular form? So I'm going to let you see if you can figure that out. Is number 1, let's just kind of figure out what tangent of theta equals. So basically, if you took the inverse tangent of 4, let's see what that's going to be. And times 180 over pi. I think that's going to be, 70. Theta is going to be roughly 76 degrees. So let's say we just kind of drew that. 76 degrees is going to look just like that. Now, tangent of theta, that's y over x, equals 4. Well, basically, we multiply both sides by x. What we get here is y equals 4x. And that looks pretty steep. So it all fits. Now, for this next one, this one's a little odd, but I'm going to give you a little starting point. Take the tangent of both sides for this one. So basically you have tangent of theta equal to tangent of pi over 4. Well, y over x is going to equal, the tangent of pi over 4 is simply 1. So y equals x. Now, if we have theta equal to pi over 4, it's just like this. And that's what it looks like, plain and simple. All right, how about you try this next one? R equals 2 cosine of theta. For something like this, start off by multiplying both sides by r. All right, so basically, here's what's going to happen. You have r equal to 2 cosine of theta, and if we multiply both sides by r, you have r squared equal to 2r cosine of theta. So, the r squared gets replaced with x squared plus y squared, and r cosine of theta gets replaced with x. So, what we need to do now is let's move this 2x over here, and you will have x squared plus 2x, and I'm leaving a little space here, not plus, but rather minus, my mistake. Plus y squared equaling 0. So, what you're going to end up doing here is completing the square. Now, we lucked out here because all we have to do is complete it for x. In some cases, you'll have to do it for both x and y. Now, we've done this sort of thing way back at the start of the course. So, what's going to complete the square for the x? Half of negative 2 is what? Negative 1, and that squared is? So, nothing for the y here, so this becomes x minus 1 quantity squared plus y squared equals 1. We have a circle, and it would be centered at 1, 0 with a radius of 1. So there's that. Now, we're going to do the same thing, except now you're going to have to complete the square for both sides, so you'll get to multiply both sides by r for this one. Convert this into a rectangular equation, and for this one, simply multiply both sides by r. Here. So what we'll do here is, multiply both sides by r, so you'd have r squared equal to r times negative 2 cosine theta minus 4 sine theta, and we distribute the r over here, so you have negative 2r cosine of theta minus 4r sine of theta. Now, we can replace the r squared with what? X squared plus y squared, and that will equal negative 2, but instead of r cosine of theta, we replace the r cosine theta with x, and minus 4, r sine of theta gets replaced with y. So we move everything over to the other side. You have x squared minus 2x plus blank, not equal to, rather, but plus y squared plus 4y. That should have been plus 2x. because these are both negative and we added it to both sides. And that should not be x, that should be y. And what you're going to see here is you're going to have to complete the square here. So to complete the square for the x, you're going to end up adding 1 to both sides. And for the y, you will add 4. So basically this becomes x plus 1 quantity squared plus y plus 2 quantity squared equal to 5. So the circle is going to have a center at -1, -2, and the radius is going to be the square root of 5, which is 2 point something. Now, again, one thing you can do here is you can get onto your calculator, which I have not done yet. I don't know why I didn't do that, but we're going to fix that. And we're going to graph that just to see that it works. Spoiler alert, it really should. So let's see what happens here. First off, mode. Yeah, I'm going to make sure I'm in polar mode here. So then, oh, it didn't work. Try that again. There we go. So yeah, you have -2 cosine theta minus 4 sine theta. And let's take a look here. It's going to be centered at -1, -2. Yep, that's about right. Now, when you have something like this, take tangent of both sides. What will happen? So if we took the tangent of both sides, and it's tangent of theta equal to tangent of 5 pi over 6, here's what happens now. Tangent of theta is just y over x, and if we took the tangent of 5 pi over 6, let's see here. Of course, I probably should know that off by heart, and I think that's going to be -√3 over 3. So y will literally equal -√3 over 3 times x. So 5 pi over 6 is 150 degrees, and it'll pass right through the origin. And it's kind of hard to tell here, but yeah, we know it's going to be a negative slope, so that's why it goes down from left to right. The slope is a little bit more than -1/2. So if you went down 1, you go just over 2 here. So yeah, it kind of fits. So how can we grab? Oh yes.
No, it flips it.
It would kind of flip it, yeah.
Because I got like 69.09 when I tried to.
Well, negative pi over 6 gets you the same thing. It is basically the same thing. So if you gave me, but see, what I was looking at here, now you had to take the tangent, not the inverse. Now, if you took the inverse tangent of this, yeah. But the main idea was to convert this to a linear equation. Yeah. But if we wanted to actually, so good question. If I said to write this in polar form, well, you could just divide by x and you would get tangent of theta equal to -√3 over 3. And technically, theta would be negative pi over 6, which technically it's not wrong. So I wouldn't dock you. So yeah, answers can vary, so to speak. All right, any other questions? Good question there, great question. All right, so we've talked about how to graph polar equations on the calculator, and that for the most part is what we're going to limit it to. In other words, we're not going to be graphing from piece to piece here. So right now we are in polar mode, and if you hit second and zoom for format, you can actually switch between rectangular and polar coordinates. So we're also going to kind of switch this off to polar in a way. So what you'll see is you'll have an R, you'll have theta, and you'll be able to figure out, R and theta. And so here's what we're going to do. We're going to graph the function R equals 6 sine of theta. So we're going to do theta incrementally in multiples of pi over 6. And we're going to generate some coordinates here. Now, so when theta is 0, R is simply going to be 6 sine of 0. R is going to be 0. So R theta is just going to be 0, 0. So yeah, 6 sine of theta. So what I want you to do is find the other coordinates for this. Do pi over 6, R will be 6 times the sine of pi over 6, so R will be 6 times 1/2, or 3. So this is going to be 3 with pi over 6. So it's going to show up right about there. Now for a couple of these, you'll get radicals. Don't worry too much about that. Just kind of get a decimal equivalence of those. So in this case, you have 6 times the sine of pi over 3. Well, the sine of pi over 3 is root 3 over 2. So it's going to be 3 root 3. So you have 3 root 3 pi over 3. Now, 3 root 3 is approximately 5.2. So let's see here. It's 2, 3, 4. Wait. 1, 2, 3, 4, 5.2. Right about here. And I just lost that. There we go. All right, so now 6 sine of pi over 2. Well, the sine of pi over 2 is what? Yep, so that's just going to be 6. So now you have 6 times the sine of 2 pi over 3. Well, the sine of 2 pi over 3 is what? Root 3 over 2, which is 3 root 3. So you have 3 root 3 again, and this time you're at 2 pi over 3. So that's going to be 5 and change, and it'll look like that. Then 5 pi over 6, you have 6 times the sine of 5 pi over 6. The sine of 5 pi over 6 is 1/2. So it's just going to be 3. Let's see. 1, 2, 3. And then for pi, 6 sine of pi, well, that's basically 0. 0 and pi here. So here's the thing, though. When you notice there's 6 points here, and if you actually connected those 6 points, a little bit of a problem, so to speak. If you actually connected those the way it shows, that would be a hexagon. Now, if we went to trace, and actually if we go to window, now basically you have a parameter here of theta, and if we made the theta step pi over 6, so yeah, go to window, and theta step is going to be pi over 6 in this case. So what that means is it's going to do it every pi over 6 units. And let's see what we get here. Yeah, we get a hexagon. Now, you can make that theta step as small as you want. Now, there is a bit of a drawback to that. For instance, if I made the theta step like 0.01, it doesn't take forever to do that. Like if I did 0.001, yeah, that's going to take a moment. But it's very detailed in that case. Now, if you notice, my thing was still going because I went from 0 to 2 pi. Now, if I just took it to pi, you'd really literally only need to make one revolution here. I know one revolution is 2 pi, but it's the nature of the equation. But if I took that to, say, 4 pi, see, it's literally going to draw over itself. There's one, and there's a second one going. But if you can see, this thing means it's working. And believe it or not, that actually, when it's working like that for lengths of time, that actually eats up battery.
It's just redrawing the circle on top of it.
That's basically what it's doing, yes, but it is still working, is the idea here. Yeah. I'll tell you, I do like how these calculators have a rechargeable battery, but what if you're in the middle of something and your battery goes dead, and you've forgotten to charge your calculator? Well, see, when I was in college, you're going to think I was a big dork, and then you're going to think I'm an even bigger dork. I carried spare batteries with my calculator. Not only that, I actually carried a spare calculator. Yep. I was like that. So, all right. So, basically, if you want to verify that this is, in fact, a circle, r squared would be 6r sine of theta. And we're just going to verify x squared plus y squared equals 6y, or x squared plus y squared minus 6y. And if we add 9 to both sides of this is literally x squared plus y minus 3 quantity squared equal to 9. So the center is going to be at 0, 3, and the radius is going to be 3. Well, we saw that before. Now, before we move on here, so if I had this stopped at, say, pi over 2, it's only going to go halfway. See, it's going to stop. 2 pi is a good rule of thumb for that. And if you change this to rectangular coordinates and did window, yeah, basically it's going to display this no matter what here. But choosing between rectangular and polar coordinates, the purpose is, you're just going to have it displayed. In this case, right now, like if you enter theta like 2 or whatever, it gives you the rectangular coordinate. But if you switch it to polar coordinates, following the steps that are on your notes, it'll display the polar version. All right, so basically r equaling a sine of theta and a cosine of theta are, in fact, going to be circles. Now, these are just some symmetry tests And the good thing is we're not really going to worry so much about this because, frankly, the symmetry tests have also been known to not work. I know, it seems really like silly. Like, why would they not work? So in other words, if a polar equation happens to fail a symmetry test, it does not disqualify it from that particular symmetry. So we can literally use our eyes here. So if we had r equal to, oh, first off, I'll explain how it works here. So if it was symmetric with respect to the polar or x-axis, if you replaced with theta with negative theta and got an equivalent equation, then it is going to be symmetric with respect to the polar axis. I'm actually, I don't put symmetry on the test because there's just so many oddball things, but we're still going to, play with it here. Believe it or not, yeah, we have a lot more in this unit to cover. Now, if we had it symmetric with respect to the line theta equals pi over 2, or the y-axis, if you replace both r and theta with negative r and negative theta and got the same thing, then it's going to be symmetric with respect to the y-axis. And then origin is where you would replace r with negative r. Now, let's keep this in mind here. 6 sine of theta is obviously going to be symmetric about, let's see here. It looks like it's going to be symmetric about the y-axis, definitely not the x-axis. So if we wanted to test it with x-axis or polar, what we would simply do is r equal to 6 sine of negative theta. So we replace the theta with negative theta, and if you took the sine of negative theta, what does that become? Yeah, negative 6 sine of theta, not the same. And it's quite obvious that, yeah, here's your x or polar axis. It's definitely not symmetric. Now, if we wanted to do where theta equaled pi over 2, or the y-axis, theta gets replaced with negative theta, and r gets replaced with negative r. So you start off with r equal to 6 sine of theta, and r becomes negative r, and you have 6 sine of negative theta. Well, negative r is negative 6 sine of theta, or simplifying that, r is going to equal 6 sine of theta. And it's the same. And we can also see with our very own eyes that it is in fact symmetric about that. Now, we're going to do 2 plus cosine of theta. So what you can do here is test for x or the polar. Now, here's the cool thing. You can graph 2 plus cosine of theta on your calculator. And let's see what that'll give us. It's going to take a couple of moments, but we'll get there. Okay, this looks to be kind of goofy looking. But in taking a much closer look at this, it looks to be, it might be symmetric about the x-axis, definitely not about y, and definitely not about origin. So, r equaling 2 plus cosine of theta, theta becomes negative theta. So r becomes 2 plus cosine of negative theta. Well, cosine of negative theta is equal to what? Cosine of theta. And it's the same. Yeah, your graphs of polar equations on the test will literally involve matching. It's literally going to be like the only time I'll ever ask you a multiple choice question. Or I might just do matching. I don't know what I'll do. Let's see what we can do here. All right, now, we can definitely see it's not going to be symmetric about the y-axis, but let's just kind of prove that it's not. Negative r equals 2 plus cosine of negative theta. Negative r will equal 2 plus cosine of theta, so that's a no. And the origin is where you replace the negative r, and that is not the same. So, there are some characteristics of these polar graphs that you don't really have to memorize. But you're going to have, these are called limacons, and a plus b sine of theta and a minus b sine of theta, both a and b are both positive numbers. And you'll have, and basically the ratio a over b will determine the shape. So, what was that previous one that we just did that was 2 plus sine of theta? So, yeah, 2 plus 1 cosine of theta. So, a is 2 and b is 1. So, a over b is going to equal 2. And literally what happens here is it'll have no dimple and no inner loop if a over b is greater than or equal to 2. Now, if the a over b was between 1 and 2, then it would be dimpled. So basically, these limacons, they're literally going to be symmetric solely across the x-axis. And you'd have an inner loop here. So what you can do is literally play with a over b and graph some of these. So yeah, let's not worry about testing that for symmetry, but graph 4 plus 3 cosine of theta for me and put the theta between 0 and 2 pi. That'll be kind of the industry standard here. No point in memorizing this here, but A is 4 and B is 3. So A over B is equal to 4/3, which is between 1 and 2. So it's going to be it's going to be dimpled. So let's see how that holds true. 4 plus 3 cosine of theta. So it looks to be slightly dimpled, but although I would probably even call that a heart shape almost. Now, let's just see what happens if I change that. I don't know, 4 plus 4 cosine of theta. Yeah, the red one is much more heart-shaped. So if you take notice here, yeah, it really kind of digs itself in. I guess you could call it heart-shaped because it really goes into the origin here pretty much. But yeah, if you notice the blue one could argue that that is heart-shaped in a way, but yeah, that's why I wouldn't actually test you on this, but it's still kind of cool. I wonder if yeah, I wonder if transforming actually works with this. Like if I did, something tells me that it's not going to. But if I did A plus B sine of theta, I'm just going to play with that for a second, see if that really works or not. Well, it does, yes. And it doesn't look like the transforming thing works. All right, so basically, let's just get out of that then. Forget I ever said that, I'm sorry. So 4 plus 3 cosine of theta. Well, all of these limacons look to be cosine shaped, and they're going to be symmetric about the x-axis. Now, I think if it's a sine one, you can assume it would be about the y-axis. So yeah, let's see here. Yep. All right, so I want you to try 4 cosine of 3 theta. You want, no, let's do this one here. Let's actually do r equals, 3 plus 4 sine of theta. Yeah. So yeah, this is definitely symmetric about the y-axis here. So yeah, if it's sine, it's symmetric about the y-axis, but the a value, the ratio is 3/4, so you're going to have an inner loop in that case. So that's what that's going to look like. Now, if you graph r equals 4 cosine of 3 theta, and here's the thing, 4 cosine of 3 theta, and if you notice, theta is going to go between 0 and pi. So it might take a hot minute, but it's going to look something like this. Now, obviously, it's not going to be symmetric about the y-axis, but could it be symmetric about the x-axis? Well, let's take a look. So basically, you replace theta with negative theta. So r equals 4 cosine of 3 theta will become r equals 4 cosine of negative 3 theta. Well, cosine of negative theta just becomes what it was, so 4 cosine of 3 theta. So it is, in fact, symmetric about the x-axis here. Now, could it be symmetric about the origin? I don't think so. Well, let's see here. Yeah, the origin symmetry is actually, yeah, the pole. So let's replace them. If we replace them both, not both, but for the origin, r becomes negative r. Was that right? Yeah. I just lost my train of thought. Yeah, I replace r with negative r. And let's see here. So you have negative r equals 4 cosine of 3 theta. The answer is no. All right, so now you have that. Now, if you notice, this one had, I guess you could call it leaves or whatever, but I want to see what happens before we move on. You know, I said between 0 and pi. If I took this to 2 pi, I wonder what would happen. Oh, it just draws over itself. So that's okay. But it's basically more or less the same exact thing as before. So if you have r equals a sine of n theta and r equals a cosine of n theta, those are going to be rose curves. So if n is even, the rose is going to have 2n number of petals. So for instance, yeah, if it's sine of 2 theta or cosine of 4 theta, yeah, it's double. And if n is odd, then it's just going to have n number of petals. And I think what that a is going to do, so if we go back and draw this, let's say we made the next one 5 cosine of 3 theta. It literally is just a dilation or an expansion of the previous one. That's all there is to it. Yeah, I mean, in all my years of studying in math, I honestly never did a whole lot with polar stuff like this. Now, we're going to see, yeah, we're going to get into complex numbers tomorrow, and that's a big thing, because I think you're going to really like that. And graph this one. Yeah, 6 sine of 3 theta. So yeah, that's going to have 3 petals, and that looks like it's going to be symmetric about the y-axis. Now, if I actually change the theta step to like 0.5, look at that. Yeah. And of course, if I did like 24 pi, let's see here, would it actually have to think? Whoa. Yeah. But like, yeah, 0.01 would be probably more than sufficient. Yeah, there you go. All right, so with that in mind, that's what we've got here. All right, we're going to go ahead and when it comes to this polar graphing stuff is when it comes time for a unit test, I'm basically just going to, it's going to be a matching type question. You're going to match it with whatever graph you seem to want to make it fit here. Now, with the polar graphing that we've been doing here, everything has always been in terms of r. But if you notice here, you have an r squared. So, obviously, if you want to solve this for r, what you simply need to do is take the square root of both sides. Easy enough. So here's what we'll see here. So basically, if you have, r squared equals 4 cosine of 2 theta, if we take the square root of both sides, here's the thing. You have r equal to plus or minus, because remember, and here's what happens here. Basically, when you're taking the square root of something squared, the other side is going to be plus minus, because basically this part here becomes the absolute value of r. And basically, because that's an absolute value, you could just take the plus or minus. And you could factor out a 2 if you want there, but you can just kind of leave it like this. So how would we go about graphing that? Well, that's actually pretty easy to do. So when we go to polar, we'll simply graph the square root of 4 cosine of 2 theta, and then negative 4 cosine of 2 theta. And I'll change this like to 0.01. And basically, it's going to take a shape like this, like an infinity symbol. Well, that's easy enough here, because what happens, there's kind of another rule here as it pertains to this, where if you have r squared equal to a squared cosine of 2 theta, it's going to be symmetric with respect to the polar axis and the pole. But if you had it as a squared sine of 2 theta, that's going to be symmetric with respect to the pole. It's going to kind of be an infinity symbol on its side. So, for instance, let's kind of graph that here. Let's just change that to, like, say 9, and instead of cosine, we'll do sine. So 9 sine of 2 theta, and it's going to look like that. So not a whole bad thing. Now again, the whole thing with polar graphing, I'll be perfectly honest, there isn't a whole lot to do with polar graphing unless you're in a more specific area of mathematics. And again, I'll be perfectly honest, aside from teaching it at this level, I can't even remember at any time where we really did a whole lot of it. But it's always good to be able to convert rectangular to polar. That's going to be the main emphasis of our unit, and polar to rectangular. Now, with that in mind, we are now going to talk about one of my other favorite sections in this unit, complex numbers. Now, if this looks somewhat familiar to you, complex number of z. Now, here's the thing. Z is the standard variable for a complex number, much like x is the standard for a variable in algebra. Z is your standard for complex numbers. Basically, the horizontal axis of your coordinate plane is your real axis. The vertical axis is going to be your imaginary axis. And the coordinate system, you would just call that the complex plane. Now, a couple of things that we're going to ultimately do with these is we are actually going to convert these into polar form and vice versa. And the methods and the procedures for doing so are actually going to be quite familiar to you. as we're about to see. So for instance, if I wanted to plot the number z equaling 2 plus 3i, well, the real part is 2 and the imaginary part is 3, it's going to show up here. Now, we're not really going to be able, well, we could convert that to a polar form. Now, one of the little problems that we'll have with it is, yeah, the radius is going to be some really oddball number, and the angle might be a little weird. But, you know, we're going to come back to these at another point as well. And you have negative 1 minus 3i. So on the real part, you have negative 1 and negative 3 on the imaginary part. So basically, that's how we plot these complex numbers. Now, what we're going to ultimately end up doing is converting these into polar form where we figure out the radius and the angle. And believe it or not, this is all going to be very familiar to you in just a few short moments. So, what happens? How do we do this?
It's separate from, say, like the z-axis on a three-dimensional coordinate.
Yeah, this has nothing to do with three-dimensional. Not one bit. So, if you want to determine the absolute value of the complex number z equaling a plus bi, which is literally your distance from the origin to point z in the complex plane, we can simply determine the absolute value by taking the square root of a squared plus b squared. So, for example, if we wanted to determine the absolute value of z equal to 3 plus 4i, you know, the absolute value of z, I put a little notch here because otherwise my z's would look like 2's. So, every year I've been asked, why do I do it like that? Well, that's why. And a plus bi, and I draw my eyes like this with the tail because we haven't really got into imaginary numbers yet. And basically, it's going to be the square root of 3 squared plus 4 squared. Well, that's the square root of 25, which is 5. Now, for this next one, you're not going to get an integer, but I still want you to determine the absolute value. Guy. Well, that's easy enough to do, which is going to be the square root of 3 squared plus negative 2 squared, which is the square root of 13, which is 3.61 and change. Now, believe it or not, your calculator can figure out these absolute values of complex numbers. Yeah, you never thought it could do that, but it can. So if you go to math and you choose complex and you choose abs, now, of course, you could do the same thing if you go to num and choose abs. It's basically the same thing. And if you did 3 plus 4i, you would get 5. And if you did the absolute value of, was it 3 minus 2i? Now the I, if you remember from 171, is where you do that for the period here. And yeah, now if you had a computer algebra system, this would give you like square root of 13. Now, let's actually kind of step back. And I want you to find the absolute values of both of these. Out the absolute value of 2 plus 3i, well, that's square root of 2 squared plus 3 squared, which is the square root of 13, which is approximately 3.61. And if we actually drew the line, it would actually have a length of 3.61 units. Now the absolute value for this one, let's see here, you have negative 1 squared plus negative 3 squared, which becomes a square root of 10, and square root of 10 is something over 3. It's 3 and change, 3.16. And it's going to look just like this. There we go. So yeah, it would have a length of 3.16 units. Now, even though basically that's the distance from the point of origin to the complex value. Well, guess what? There's also, believe it or not, another name for that, where we have z equal to a plus bi. That is in rectangular form. Well, if we wanted to convert that to polar form, we would use z equal to r times cosine of theta plus I sine of theta, and it looks like r cis theta. Basically, the cosine of, bless you, the cosine of theta, cosine is your horizontal axis or your real axis. The sine is your vertical or your imaginary, and that's why the I comes from there. So basically, what you have to do here is, you have A equal to R cosine of theta, B equal to R sine of theta, R equals the square root of A squared plus B squared, which we've already established is the absolute value or the distance. And tangent of theta equals B over A. So R is technically known as the modulus of the complex number Z, and the angle theta is known as the argument. So we're going to start off with something relatively simple here, even though, you see a radical here. But what's going to happen is the R value should be something easy. And we can also make a drawing here. We're going to convert this because we're going to stick with a first quadrant one to start. I don't know what I was smoking when I drew that up. Nothing. I've never smoked a thing in my life, so I don't even know why I said it, but I did. Anywho, so basically we want to figure out R here. And now the angle is also going to depend on what quadrant you're going to be in. Now, if you're wondering, where have I seen these kind of imaginary numbers before? Basically, they are from, if you remember, polynomials. Like a fourth degree polynomial would have how many roots to it? 4. And some of them are real, some of them are imaginary. So what we're going to do here is we need to figure out the R value first, which is the square root of 2 squared plus 2 root 3 quantity squared. Now, you can also kind of draw that in a way to also help you figure out what the angle is going to be. So the first thing we do is we want to figure out R. Now, for problems like these, the R value is simply going to be a nice number. The R value is not going to involve some radical or anything like that in the end. But this is, 4 plus 12, which is the square root of 16, which is 4. So that is our R value of 4. Now, what we want to do here is figure out the angle. Now, here's the thing. The nice thing is, tangent of theta is simply going to be 2 root 3 over 2. But believe it or not, if you draw this out, you could even use a sine or a cosine ratio. So nonetheless, if the tangent of theta equals the square root of 3, we would take the inverse tangent of that. You could take the inverse tangent of the square root of 3. And we get, and I think that's pi over 3. Yep. So basically, here's what happens. Yeah, 2 plus 2i root 3. 2 root 3, that's approximately, what? That's like 3.46. So yeah, 1 and 2, 2, 3, 4. So it's going to be right about here. Oh, too far. I'll get this one way. I'll get it. Okay. Oh, too far again. You know what? Close enough. So basically, this is going to be a 4 here, and the angle is pi over 3, or 60 degrees. So basically, you have 2 plus 2i root 3 will equal 4. What the heck? It'll equal 4 times cosine of pi over 3 plus I times the sine of pi over 3. But you can also write this as 4 cis pi over 3. Because the cis comes from cosine I sine. All there is to it. Now, if you actually did 4 times cosine of pi over 3 plus I times the sine of pi over 3, or 60 degrees, you would get 2 plus that. And 2 root 3 is 3.46. But that's how this is all going to work. So I want you to try the next one. So the first thing we'll do is we'll figure out what r is. Now, since both of these are positive, this is going to end up in the first quadrant. So r is going to be the square root of 3 root 2 quantity squared plus 3 root 2 quantity squared again. So let's see here. That's 9 times 2. That's the square root of 18 plus 18, which is the square root of 36, which is 6. So that's going to be our value of r. Now, here's the thing. So basically, the real and the imaginary component are literally the same value. And we can even do a trig ratio to kind of figure this out here. But what happens here is, this is where z is 3 root 2 plus 3i root 2. And this is a value of 6 here. Now, theoretically, you could just do a tangent. Tangent of theta would equal 3 root 2 over 3 root 2, which is 1. And theta is just going to be pi over 4. So basically, 3 root 2 plus 3i root 2 is literally going to be 6 cis pi over 4. Now, we're going to change this next one. Let's make this a little more entertaining. Instead of this, we'll do 3 root 3 minus 3i. So Casio is for statistics. It's not as user-friendly, but it technically does a little more. But here's one of the reasons I kind of like Casio. So if I did, 6 times cosine of pi over 4, let's see, I haven't used Casio in a while. Yeah, it has been a few days. Oh, wait. I forgot I can do a fraction here. Yeah, see, Casio actually came up with this a little bit earlier. And for some reason, yeah, this thing is just not responding the way. Yeah, pi over 4. And here's the thing. Here's the purpose of that. It actually gives you the radical version, which I think is kind of cool. But, yeah. All right, give you another minute on this. All right, so for this one, R is simply going to be the square root of 3 root 3 quantity squared plus negative 3 squared. So let's see, that's 9 times 3. That's going to be the square root of 27 plus 9, which is the square root of 36, which is going to be 6. Now, this R value that you have will always be positive, by the way. It can never be a negative value. Now, one of the slight little issues, well, not really a slight issue, is if we draw this, it's going to be in what quadrant? 3 root 3 minus 3i? It's going to be the 4th quadrant. So it's going to be somewhere around here. Now, I'm going to be very specific. And what do I mean by that? Is I want the angle between 0 and 2 pi. So here's the thing. This is a 6. And, I have a 3 root 3 here. And technically that's a negative 3 here. Now, what I could do is, tangent of theta would be, well, technically, negative 3 over 3 root 3. And that's negative 1 over root 3. Now, if we did the inverse tangent of this, negative 1 over the square root of 3, we're going to get negative pi over 6. But, as I said, the angle I want is going to be between 0 and 2 pi. So, negative pi over 6, though, is the same thing as saying what? 11 pi over 6. So basically, 3 root 3 minus 3i will be 6 cis 11 pi over 6. Now, one of the other things that can be done here is, I could have done, sine of theta equal to, 3 over 6. Now, the thing is, I didn't take the negative of that, but you would get theta equal to pi over 6 in that case. But you have to know what the angle is. That's basically what it all comes down to. If I did, negative 1/2, I would get, negative pi over 6, same thing. But, so converting these to, from rectangular to polar form, is pretty straightforward, I think. And, believe it or not, let me see something here. If I did...
So the purpose of showing, for the purpose of showing our work whenever we're doing this, we won't have to rationalize the denominator.
No.
I did it out of habit.
See, if you actually go to angle, it'll also give you that. I won't lie. I mean, but you really should use a trig ratio to figure that out. Yeah. All right, so, yes? No. What I'm doing here to figure out that 6 is I'm taking the sum of the squares of these two. The square root, basically using the Pythagorean theorem. So it just happens to be a real coincidence that this was a 6. That those 3's make that a 6 in some way. Yeah, you have to do the whole thing with the R. So yeah, I see your point here, like those 3's and then that's a 6. That's just a real coincidence. Trust me on that. All right, so with that in mind, you can convert these to rectangular form. That's pretty easy to do. So basically, you have 4 cosine of pi over 4 plus I sine pi over 4. And that's going to be 4 times root 2 over 2 plus I times the sine of pi over 4 is root 2 over 2. And distributing this, you get 2 root 2 plus 2I root 2. And yeah, the fact that all these are 2's and that's a 4, yeah. Just the way it all works. I want you to try this next one for me. Basically, yeah, you do 6 times cosine of 150 degrees plus I times the sine of 150 degrees. So cosine of 150 degrees is going to be what? Now, by the way, you would have a unit circle for this per standard, but the cosine of 150 degrees is going to be negative root 3 over 2 plus I times, what's the sine of 150? 1/2. So 6 times negative root 3 over 2, well, 6 divided by 2 is 3. So it's going to be negative 3 root 3 plus 3I. Now, I'm going to give you this next formula for your test. And you're probably thinking, why am I giving you all these formulas? Well, number one, you got to know what to do with these formulas. And that's kind of my emphasis here. But if we wanted to multiply two complex numbers, such as z sub 1 equal to r sub 1 times cosine of theta 1 plus I sine theta 1, or the sis's, and R2 is this, basically when you multiply two or more complex numbers, what you're going to get here is you multiply the modulus, or the moduli, R1 and R2, and you literally add the angles together. But what we're going to do here is I also want you to convert both of those polar values to rectangular. Now, we've already done that actually for 6 cis 150, which we'll call z sub 1. That's going to be negative 3 root 3 plus 3I. Now, if we do z sub 2 equaling 4 cis pi over 3, that's going to be 4 times cosine of pi over 3 plus I sine pi over 3. So you figure out cosine of pi over 3, and that's going to be a half. And the sine of pi over 3 is what? Root 3 over 2. So this becomes ultimately 2 plus 2I root 3. Now, here's what we're going to do. You might think I'm nuts here, but now if we do z1 times z2, we're going to see how it works both ways. So basically, as we know, that's R1 times R2 times cis theta 1 plus theta 2. So the R1, the modulus for the first one was what? What was the modulus for the first complex number? 6. So 6, and what's the modulus for the second one? 4. Now, if you notice, one's in degrees and the other's in radians. So pi over 3 is how many degrees? 60. So basically 150 plus 60, this is going to equal 24 cis 210 degrees. Now, that basically means it's going to be 24 times cosine of 210 degrees plus I sine of 210 degrees. Now, FYI, 210 degrees puts us into what quadrant? Third quadrant. So, the cosine of 210 degrees is going to be negative root 3. Let's change that. Negative root 3 over 2 plus I. The sine of 210 is what? Negative 1/2. So basically, we have negative 12 root 3 minus 12I. Now, here's something that, and we're good here, but here is something that I want to do that you may or may not remember. If you multiply two complex numbers, negative 3 root 3 plus 3I times 2 plus 2I root 3. You can FOIL this, but I would honestly prefer to make a grid. So you have negative 3 root 3 plus 3I, and then you have 2 and 2I root 3. So when you multiply 2 by negative 3 root 3, what does that give you? Just 2 by negative 3 root 3. Negative 6 root 3. Very good. 2 times 3i. 6i. Now, 2i root 3 times negative 3 root 3. Well, when you multiply numbers like this, 2 times negative 3, you multiply the wholes and the radicals. 2i times negative 3 is negative 6i, but the square root of 3 times the square root of 3 is what? What's that? Not square root of 6. Square root of 9, which is 3. So negative 6i times 3, that's simply negative 18i. And 2i root 3 times 3i, that's going to be 6i squared root 3. Now, how many of you remember what I squared would be? Negative 1. Excellent. Because I is the square root of negative 1. In fact, imaginary numbers were invented in the late 1500s by Cardano, even though Euler technically got the credit for it. But see, mathematics back then was all like plagiarism and stealing, even hundreds of years ago. So negative 1 times root 3, and that's negative 6 root 3. So combining all of our like terms, here's the thing. Negative 6 root 3, negative 6 root 3, that's negative 12 root 3. And negative 18i plus 6i would be negative 12i. Now, all right, so what we'll do here is I want you to basically figure out z1 times z2 here. Now, you can put them in put both of those into polar form, and we can work with it there. All right, so for R1, we want to go ahead and take the square root of 2 root 3 quantity squared plus 2 squared. And let's see here, that's going to be 12 plus 4, which is the square root of 16, which is 4. So yeah, you see the 2's there, and that's going to be a 4. Yeah, yeah. Now, let's look at this next one. This next one for R sub 2 might be a little more entertaining. Yeah, 5 root 3 over 2 quantity squared plus 5 halves squared. And let's see here, that's 75 fourths plus 25 fourths, which is 100 fourths, or the square root of 25, which is simply going to be 5. So there's your R sub 2 value. Now let's go ahead and figure out the angle for each of these. So for Z1, yeah, I always draw it anyway here. So 2 root 3 and 2. Come on, why are we doing this? Yeah, there we go. And so the good thing is, and again, what was I thinking? That's a 4. So what we're going to do here is figure out what this angle is going to be. And one of the reasons I drew it is simply because we don't even necessarily have to use a tangent ratio. We could have just said, sine of theta equals 2/4 or a half. And if we take the inverse sine of 1/2, I think this angle is going to be pi over 6. So theta 1 will be pi over 6. Now for this one, 5 root 3 over 2 and 5 halves, 5 root 3 over 2, that's going to be a little bit more on here. 5 root 3 over 2, and then 5 halves, and of course this is going to be a 5 here, and 5 halves divided by 5. So basically theta 2, you should actually get the same thing, because 5 halves divided by 5 is a 1/2, so that's going to be pi over 6. So basically this first number in polar form is 4 cis pi over 6, and the second one is 5 cis pi over 6. So when you multiply these two numbers together, you multiply the r values and add the angles. Well, 2 pi over 6, and that becomes 2 pi over 6 or pi over 3. So that's the polar form. Now you could write it out in the lengthy matter, and I learned this writing it in cis form as a shorthand method from my former department head. So basically you could just take 20 times cosine of pi over 3 plus I sine pi over 3. Well, what's the cosine of pi over 3? 1/2. And sine of pi over 3 is root 3 over 2. So this is going to be 10 plus 10i root 3. And if you multiplied both of the complex numbers together, that's what you would get. Now, of course, your calculator would not give it to you in like the I root 3 form, but that's what we're going to get here. All right, so that's that. Now, if we want to divide both of these, divide complex numbers, well, believe it or not, you'll divide the modulus values and subtract the angles. So what you're going to do here, we're not going to do this every single time here, but the purpose of this polar cis form is to see how everything is going to gel it all together. So basically convert both of these to polar form, and the Z1 is going to be interesting. It's just going to be like 3 pi over 2 for the angle. So you'll have that. So yeah, convert both of these guys into polar form and work it out. So for R1, that's actually going to be really simple. It is going to be 12, but I'm going to show you how. Basically, Z1 is literally 0 minus 12i. So basically, if you just took the square root of 0 squared plus negative 12 squared, it's just going to turn out to be 12. I mean, so did we even have to go through that? No. But did it break our back to do it? No. All right, so we need to figure out the angle. So here's the thing, negative 12i is down here. And I'm going to be specific, the angle should be between 0 and 2 pi. And you don't even need to do any kind of inverse tangent thing. What's the angle going to be? 3 pi over 2, plain and simple. Now for the next one, that's not as cut and dry, but it's going to put us into the third quadrant. So R2, will be the square root of negative 1 squared plus negative root 3 squared. Well, here's the thing, R2 is going to be the square root of 4, which is 2. Now, that's going to put us, this is going to put us into the third quadrant here. And it's going to be somewhere down here, so to speak. So here's the thing. If we took, tangent of theta equal to negative root 3 over negative 1, which is square root of 3, and if we took the inverse tangent, here's the thing. You took the inverse tangent of the square root of 3. Well, I don't even know if I need to close. Yeah, see, theta in question is going to be pi over 3, but obviously that's not right. And the reason is simply because we need a third quadrant angle here. So theta is actually going to be 4 pi over 3. Now, here's the thing. Yeah, if you took the tangent of 4 pi over 3, you would get square root of 3. So basically, R1 or Z1 is simply going to be 12 cis 3 pi over 2. Z sub 2 is going to be 2 cis 4 pi over 3. So, if we want to figure this out here, finding the difference in the angle is going to be the fun part. Z1 over Z2 is simply going to be 12 over 2 cis 3 pi over 2 minus 4 pi over 3, which becomes 6 cis. Let's see here. That would be 9 pi over 6 minus 8 pi over 6, or simply 6 cis pi over 6. Now, here's the thing. So what I want you to do now is let's figure out, 6 cis pi over 6. That's going to be 6 times cosine of pi over 6 plus I sine pi over 6. So cosine of pi over 6 is going to be root 3 over 2. So basically you have 6 times root 3 over 2 plus I times a half. And what you're going to get here is 3 root 3 plus 3i. Now, with that in mind, if we actually divided these two complex numbers, which were, what was that, negative 12i, in other words, yeah, I'll show you what happens here. So yeah, negative 12i, and if we divided that, the long way, negative 1 minus I root 3. Now, not sure if you remember this, and this is the only time we're really going to do it, but if I wanted to get rid of that, rationalize the denominator, I need to multiply the numerator and denominator by something. And what do you think that something is going to be? Negative 1 plus I root 3 is exactly right. Very good. Now, the next question is, what is that called? Exactly. You all knew your 171 very well. So we're going to multiply the top and bottom by -1 plus I root 3 and -1 plus I root 3 down here. Now, the good thing is for the denominator, if you do that in the calculator, here's what happens. Watch this. I root 3 and -1 plus I root 3, and we get 4 on the bottom. Now, on the top, you have 12i and -12i times I root 3. That's going to be minus 12i squared root 3. Well, I squared is -1. So basically, it's going to be 12 root 3 plus 12i over 4, or 3 root 3 plus 3i. And that's it. So the purpose of going through all this was to verify that, hey, it all worked. So here's what we're going to do now. I want you to find the quotient of these two. All right, so yeah, z1 over z2, that's basically going to be 30 over 20 times cis of 120 minus 30, or 3/2 cis 90 degrees. So let's see what we got here. 3/2 times cosine of 90 degrees plus I sine of 90 degrees. Well, cosine of 90 is what? So basically you have 0, and sine of 90 is, so yeah, 0 plus 3/2 I. But if you gave me just 3/2 I, it's all good. So that's how that works. Pretty simple, pretty cool. Now, what if we wanted to find a complex number raised to a particular power, such as z to the n? Now, the conventional method would be to take the rectangular form and raise it and use the binomial expansion formula. But thanks to de Moivre's theorem, which is this, z to the power of n is simply going to be, where if you convert that z to cis form, r cosine of theta plus I sine of theta, basically you take that modulus r and raise it to the power of n. And you literally multiply the angle by n. Now, the other thing is I'm going to ask you to do, and you could probably take a good guess, is give me the angle between 0 and 2 pi. So, if we wanted to do z equals 2 plus 2i root 3, now the conventional method uses the binomial expansion formula. Now, how many of you have no idea what this is? Yeah, it's Pascal's triangle, and what happens is when you expand a binomial such as this, these are going to be the coefficients. You get Pascal's triangle like 1 and 1 is 2, 1 and 2 is 3, and so on. So if we wanted 2 plus 2i root 3 to the power of 5, the expansion, we would let a equal to 2 and b equal to 2i root 3. And in simplifying all this, you would wind up getting 512 minus 512I root 3. But what you can do here basically is you can convert 2 plus 2I root 3 into polar form. Polar meaning cis. So basically 2 plus 2I root 3 as polar form. Figure that out. It could be 4, but let's just verify that. I don't want to... Yeah, I could give you a case where it might not be, but yeah. But I make R an integer to make our lives as easy as possible. Well, no, I don't. I just come up with the problems. So yeah, R is going to be 4 here. And what basically happens, if you took tangent of theta equal to 2 root 3 over 2, tangent of theta equaling square root of 3, if we took the arctan of the square root of 3, we get theta equal to pi over 3. So 2 plus 2I root 3 is simply going to equal 4 cis pi over 3. Cis boom ba. That's a sound made when a sheep explodes. Cis boom ba. Where did it come from? Karnak from Johnny Carson. That was the one that made, yeah, oh, it was great. Anywho, so if we want to raise this to the 5th power, this is going to be 4 to the 5th times cis 5 times pi over 3. Now, 4 to the 5th is, let's see here, 64, 256. Oh, stop being so vain, Mr. Jarrett. Just use the damn calculator. 1,024 times the cis of pi over 3. Now let's convert that to rectangular form by simply taking 1,024 times cosine of pi over 3 plus I sine pi over 3. It's 5 pi over 3. Wow, I'm losing my mind here. There we go. Nothing happened to it. All right, so now we have 1,024 times cosine of 5 pi over 3. And this is when I wish I had a unit circle in front of me, but that is going to be a 1/2. And sine of 5 pi over 3 is going to be negative root 3 over 2. Oh, come on. And basically you have 512 minus 512 I root 3. Boom! That just happened. So, of course, yeah, you could work it out with the binomial expansion or, binomial theorem, but you don't even need to do that anymore. That's what you're going to get here. All right, now I want you to do this one for me, please. Yep. All right, so if we have 6 cis 135 to the 4th, that's going to be 6 to the 4th times cis 135 degrees times 4. And so 6 to the 4th is, well, it's 36 squared. And I think that's 1296 times cis 540 degrees. Now, I didn't include this here, but I would be specific in saying, please give me the angle between 0 and 2 pi or 0 and 360. So this would come out to be simply 1296 times cis 540 minus 360 should be 180. So basically 1296 times cosine of 180 plus I sine of 180. Well, cosine of 180 is what? -1, and sine of 180 is 0. So that's your simple answer right there. -1296. Now, here's something kind of useful. If I actually figured out, 6, actually I set up kind of a second parenthesis, 6 times cosine 135 plus I times sine of 135, and then
You went up between 0 and 180, right?
0 and 360. And I get that, -6. Oh, wait. And if I took that to the power of 4, yeah, I get -1296. I put the exponent in the wrong place. That was my mistake. But yeah, and e -10 basically means it's 0. So it's just the way this calculator works it. Now, I want you to find z to the -3 in both forms for this guy. So basically, if we take 3 cis 30 degrees to the -3, what we can do here, there's actually a whole other host of ways you can do this, but basically it's going to be 3 to the -3 times cis to the 30 degrees times -3, which is 1/27th cis -90 degrees. But you can also replace that, -90 with adding 360, and that would be cis 270 degrees. That's 1/27th, I'm sorry. Yeah, because 3 to the -3. So if you're not up on this, I mean, yeah, very brief crash course. This is 1/3 to the 3rd. If you have a negative exponent, you have it under a 1 and make it a positive exponent. So basically now you have 1/27th, cis 270, that's your polar form and you're good. Cosine of 270 degrees plus I sine of 270. No, yeah, I was right. Add 360. So cosine of 270 is what? And sine of 270, -1i. So basically you have -1/27 times I. Now, yeah, if you actually, so if we use the calculator, just, that's going to be 3 cosine of 30 degrees plus I times sine of 30 degrees And if we multiplied that or raised that to the power of -3, okay, I'm thinking maybe I did something wrong here. Yeah, -1. Yeah, 3 cis. Let me check something on my other calculator. I know I shouldn't do this, but I'm going to do it anyway. I'm going to break out the computer algebra system. Hey, I can make a mistake too. I mean, I wish I didn't, but I can. Computer algebra systems make my life so much easier. Yeah, 3 times cosine of 30 degrees and plus I times sine of 30 degrees. See, this doesn't have the QWERTY keyboard, which makes it test legal. And so that's that form. Okay, so I had to have made a mistake here. Oh. Cosine of -90. Yeah, it should have been that, yeah. No, wait. I did that right, yeah. No, you don't multiply it by -½ because that's a -1. Okay. I'll tell you what here. So let me take a close look at this here. So yeah, 3. I think I know what I did wrong here. If I type this in wrong, then I raise this to the power of -3. Oh, I was right the whole time. Oh, I think I know what I did wrong here. Yeah. I don't know what I did wrong, but yeah, obviously I didn't do everything in the book wrong. Oh, yeah. I know exactly what I did wrong. I didn't multiply the 3 right on here. And here's the thing. I can make a mistake. Yeah, I should have just put the 3 on the outside just like this times 3 and then to the -3. And if I dare get a wow,
Holy crap.
it does that. Managed to do that. Okay, well, with that in mind, we're going to talk about our having complex numbers in polar form. And what we're going to do here is we're going to have complex number, and we may have to convert that to polar form. That's okay. So our complex, which could include real or imaginary numbers, can have n distinct complex nth roots given by the nth root of r, and this will always be an integer in our case, so you don't really have to worry too much about that. Basically, we have it in both radian and degree form, where it's actually going to be probably a little bit easier to do it in degree form. And here's why, because you're going to kind of figure out a pattern to this in a way. So, if we wanted to find, for instance, the 3 third roots of w equals 125. Now, think back to your days in algebra. X to the third minus 125. Think back to how that factored. x to the third minus 125 is what we call a difference of cubes. It's going to be a difference of cubes here. And if you remember, and if you don't, that's okay too. But basically, it's going to factor into a linear and a quadratic. This being a difference of cubes, obviously the cube root of x to the third is simply x. But what's the cube root of 125? 5. So this is going to end up factoring into x minus 5. And come on. Yeah. So, and this is x squared plus 5x plus 25. This is how it's going to factor. Now, we already know that 5 is going to be one of the roots here. So if you don't remember difference or sum of cubes factoring, that's okay too. But basically, if you had a to the third minus b to the third, it's simply going to be a minus b times a squared plus a times b plus b squared. Because what happens here, this is minus a squared b, and that's going to be plus a squared b, and that's ultimately you're going to get some eliminations here, but think of soap. Same, opposite, and always positive. That's going to be your rules for the signs for this. Now, of course. So, if I wanted to solve, so basically, yeah, we know x is going to equal 5 here, but if we had x squared plus 5x plus 25 equal to 0, you can factor this, or, you can't factor this, but you can also, you can complete the square for this, or use a quadratic formula. Now, you will get imaginary roots for this. So there's no doubt about that. So why don't you try that real quick. All right, so basically, if I want to use the quadratic formula, A is going to be 1, B is going to be 5, and C is going to be 25. You have B squared minus 4AC. That'll be 5 squared minus 4 times 1 times 25, and that will give us negative 75. Now, when we take the square root of negative 75, that's going to basically be an I times root 75, which is I root 25 and 3. So this is 5I root 3. So basically, using the quadratic formula, you have negative 5 plus or minus 5I root 3 over 2, which does simplify to basically negative 5 halves plus or minus 5I root 3 over 2. Now, these two are imaginary solutions or imaginary roots, and they happen to be what of each other? They're conjugates. Now, you remember that from your 171 days. Now, let's go on and so let's talk about how to find the 3/3 roots of this. Now, let's keep this in mind here. W is going to be 125, so we want the cube roots. And there will be 3 of them. So here's what's going to happen. We'll use this one here. We'll use the one with the degrees. Frankly, there's going to be some of these where, yeah, the imaginary roots are going to be such weird degrees that you're not going to be able to convert them to a nice, clean, imaginary number that you see here. But W equals 125 in polar form is what? Well, that's going to be relatively easy to figure out here because 125 is a pure real number. So basically, the R is going to be 125 and theta is going to simply be 0 degrees. So this is simply going to be 125 cis 0 degrees. Now, of course, you're probably wondering, okay, why is it working out this way here? Why can't we just take the answer that we got and be done with it here? Well, let's keep something in mind here. Now, by the way, I will give you this formula. So we're going to figure out all of the roots, it's basically going to be the nth root of R times cis. Yeah, I'm going to write it out as cis here. Theta plus 360 degrees K over N. Now, in our case, we want cube roots. So what is N going to be? What's our value of N going to be for this one? 3. And so basically, we're going to find 3 roots. And we're going to start off where K is 0. Now, of course, there'll be problems where you're going to find more roots, but ultimately, what you're going to find is the angle will go up consistently. And here's what I mean by that. Now, the nth root of, for Z, actually, let's do this where K is 0, because K has to start at 0. So basically, we're going to find the nth root, or the cube root of 125, which we already know is 5, times cis 0 plus 360 times 0 over 3. Well, the cube root of 125 is 5, and the angle becomes simply 0 degrees, 5 cis 0 degrees. So that's the polar form of this. And the rectangular form is just simply going to be what? Five cis 0. It's just going to be 5 here. We could actually write that out here. 5 times cosine of 0 degrees plus I times the sine of 0 degrees. Cosine of 0 is what? And sine of 0 is 0I. So this is just going to be 5, which happens to match what we had before. Now we're going to get another root, K equals 1, where it's still going to be the cube root of 125 times cis 0 degrees plus 360 times 1 over 3. So basically this becomes 5 cis 360 divided by 3, that's 5 cis 120 degrees. Now, you can find the rectangular version of this very easily, where you just do 5 times cosine of 120 degrees plus I sine 120 degrees. Well, here's the thing. Cosine of 120 is what? Again, this is when negative 1/2. And the sine of 120 is what? So I root 3 over 2. And this is going to simplify to simply negative 5/2 plus 5I root 3 over 2. Now, we're going to do the one where k is going to be 2, and that will be our final one, because since we're finding the 3 cube roots, you always start with k is 0, so your last k value will be whatever n minus 1 is. So yeah, cube root of 125 times cis of 0 plus 360 times 2 over 3. Well, that's going to become 5 cis 240 degrees. Now, even though you don't exactly see it with this here, the angle went from 0 to 120 to 240. Eventually, like if we were doing, say, sixth roots, what you would find is you would see that there are more. You would see that the angle is going to go up by consistent margin each and every time. So now we figure out 5 cis 240. Well, let's keep this in mind. 240 degrees puts us into what quadrant? Third quadrant. So this is simply going to be, oh, come on, why is this thing going so slow today? All right, where are we? Let's get back to this. So basically, yeah, 5 times cosine of 240 plus I sine of 240. Well, the cosine of 240 is what? Negative 1/2. And sine of 240 is negative root 3 over 2. So this is negative 5/2 minus 5I root 3 over 2. So we have found all 3 cube roots of, we found all 3 cube roots of 125. So this should have been a positive 64 here. So so finding the 6 sixth roots of w equals negative 64. So think of solving this equation, x to the 6th or w to the 6th equals 64. What you're going to find is how many solutions should this actually have, technically? There will be 6. Now, what you'll find is, this can factor into a sum and a difference of cubes, something like that. I mean, it can be kind of messy here, to say the least. But basically, you're going to have 6 roots. So basically, find the sixth roots of 64. Now, 64, now it's not going to be this cut and dry each and every time. In other words, I'm not going to give you like a whole number each and every time. Like we're going to have one like this next one after this here. So, but 64 in polar form is 64 cis 0 degrees. So, basically, z sub k is simply going to be the 6th root of 64, which happens to be what? Two. So basically, again, the only thing that you're going to be modifying each and every time here is the k value. So basically, starting with 0, you're going to have 2 times cis 0 plus 360 times 0 over 6, which is basically 2 cis 0 degrees, which is simply just going to be 2. So you're going to find 5 more roots to this. When the k is 1. So basically, yeah. So it's going to be 2 cis. You could do, so one thing you could do, by the way, is you could do 2 cis, basically 0 degrees, because 0 over 6, plus 360k over 6. But 360 divided by 360 times 1 is 360. Yeah, 360 over 6. This becomes 2 cis 60 degrees. Now, what did you get for the angle, for the degrees? Oh, no. This angle here is 0 degrees. So the reason we have this 0 here is because of this. That's where it comes from. Yeah. So basically, 2 times cosine of 60 so basically this becomes 1 plus I root 3, or yeah, if we did sine of 60 degrees, root 3 over 2, yeah. So now we found 2 of them. All right, so if we want to find it where k is 2, you have 2 cis, and here's the thing. You could have also written this as 2 basically cis 60k. So basically this is 2 cis 120 degrees. The third root is 2 cis 180. And then for 4, it's going to be 2 cis 240. And then for the fifth and final one, it would be 2 cis 300 degrees. So even if it's a oddball root that we're going to see, like even if it's like an oddball W value, like this one here, is kind of, yeah. This one is something that you might have solved back in your pre-calc days. So 2 cis 120, cosine of 120 degrees, it's negative 1/2. So basically 2 times negative 1/2 plus I root 3 over 2, and this is going to simplify to negative 1 plus I root 3. Now for 2 cis 180, cosine of 180 is negative 1. Sine of 180 is 0. So basically you have a negative 2 here. Now 2 cis 240, cosine of 240 degrees, that's going to be a negative 1/2. And this will be minus I root 3 over 2, which makes it become negative 1 minus I root 3. And then for cis 300, cosine of 300 degrees is going to be a positive 1/2, but the sine of 300 is minus I root 3 over 2, and that becomes 1 minus I root 3. Now, here's the thing. Besides the 2 and negative 2, which are purely real numbers, we have not one, but 2 pairs of complex numbers in this whole fray. And the reason these are all going to be conjugates of each other is because, well, 64 is a pure real number. Now, for the next example that you're going to work on, you're going to want to find the 5/5 roots of this. Now, you'll be able to come up with the general form of the equation after you find the polar form of this one. And then what you'll do with that is, you'll come up, you'll come up with the roots. But these are going to be kind of oddball angles here. So your first order of business is to figure out the roots. Figure out what the polar form of that is. Is figure out the polar form of this. So we know that this is going to be a third quadrant angle. So let's see here. So basically your R value is going to be the square root of negative 16 squared plus negative 16 root 3 quantity squared. And so we want to go ahead and figure that out. Oh, not that one. So you have negative 16 quantity squared plus negative 16 root 3 quantity squared, and that's going to become 32. And yes, you could read that as, 16 and 16 make 32. But still, it's always good to figure out how you got it. And here's the thing. Tangent of theta is going to be negative 16 root 3 over negative 16. Well, that's going to simplify to simply root 3. Now, here's the thing. If we take the inverse tangent, not inverse cosine, but the inverse tangent of square root of 3, we're going to get pi over 3 here, or 60 degrees. But since this is a third quadrant deal, we want this to be you would add pi units. or 180 degrees. So basically, theta is going to be 240 degrees. So this W that we have here, it's going to be 32 cis 240 degrees. Now, for the Z sub k, it will be the fifth root of 32, which we know is going to be 2, times cis, 240 degrees over, 240 plus 360k over 5. Or what you could do, we know the fifth root of 32 is going to simply be a 2 here, times cis 240 over 5 plus 360k over 5. Well, that's a 5, not an 8. 240 divided by 5, that's going to be 48. 48 degrees, and 360 over 5 is 72. So basically, you'll start off where k is 0, and then gradually increase it up to 4. So basically, where z, for 0, k is 0, that's just going to be 2 cis 48 degrees. Now, we're not going to even think about coming up with the rectangular form of this, not without a computer algebra system, because that's going to give you some really weird value. Now, for 1, where k is 1, you have 2 cis, 48 degrees plus 72 degrees. And 48 and 72 adds to 120 degrees. Now, that could be converted to rectangular form, but we're not going to worry about that. Now, if we want to find where it's going to be, k is 2, that will be 2 cis, 48 plus 72 times 2. And that means it's going to go up by what? The angle's going to become what? Yeah, so why didn't we divide by, well, here's the thing. We divided by 5 right here. Anytime you get a problem like this, especially on your test on Monday, it will simplify to this. We went ahead and divided it by 5 right off the bat. So 2 times 72 is 144 plus 48. So that's going to be 192 degrees. Now, if you notice, we go from 48 to 120 to 192. What are we increasing by? See? In other words, we went and divided both of these arguments by 5. You could have done 240 plus 360 times, say, 2. Plus 360 times 2 and divide that by 5 and gotten the same thing. But I will always make it work so that you'll have an integer, that it'll be nothing but integers. You won't have to worry about rounding angles or anything of that nature. Third root, that's going to be 2 cis times 48 plus 72 times 3. So basically we add another 72. And this is going to be 2 cis 264 degrees. And the last one will be 336 degrees. Now, one thing that you've hopefully noticed is, yeah, we did 5/5 roots of this. We did 6/6 roots of the previous one. The angles did not get above 360 degrees or 2 pi radians. If they did, then you did something wrong. I mean, that's all there is to it. All there is to that one. So yeah, you could convert the 2 cis 120 into a rectangular form, but you don't really have to. All right, so we'll start on one more. One. Yeah, we'll get you started on this. Oh, okay. Why is this happening here? Okay, so why is my computer like lagging? Okay, come on. All right, so I want you to find the 4/4 roots of negative 81. Not positive 81, but negative 81. The first thing you'll do is W equals negative 81 in polar / cis form. W equaling negative 81 in polar cis form, well, that's easy enough to do. So negative 81 is a pure real number here. So it's just going to be this. So basically, negative 81 will literally be 81 cis 180 degrees. So you see why it's a 180 degree angle. So what we're going to do with that is very simple. We're going to use this formula here that's in front of us here. So the theta in question is going to be 180. So z sub k will be basically the 4th root of 81, positive 81, times cis 180 degrees plus 360k over 4. Now, one thing we can do here, obviously we know the 4th root of 81 is going to be what? That's going to be a 3. And we can do 180 divided by 4, which is 45 degrees, plus 360 over 4, which is 90 degrees K. So for one like this, we can get the coordinates in both polar cis form and in rectangular form. So for 0, it's literally going to be 3 cis 45 degrees. Z sub 1 will be 3 cis what? What will that one be? 135. How about z sub 2? 225 degrees. And then z sub 3, our final root, will be 3 cis. So for one like this, you can give them in both polar and rectangular form. Why don't you figure out the rectangular forms? 45. Basically, these are, so basically you have 3 times cosine of 45 plus I sine of 45. And it's going to be 3 times root 2 over 2 plus I root 2 over 2. Or basically 3 root 2 over 2 plus 3I root 2 over 2. So literally, these angles are merely going to change a couple of signs. That's all they're really going to do here. So for this one, cis 135, that puts us into what quadrant? Second quadrant. So basically, it's just going to be negative 3 root 2 over 2 plus 3I root 2 over 2. Now for 225, both are going to be negative. And then for 315, the cosine is positive, but the sine is negative. And so basically, negative 81 is an integer, and all 4 of these roots are imaginary. And we literally have 2 pairs of complex conjugates, this pair and this pair. And if you actually go into the polynomial root finder, now it won't give you these on, it won't give it to you in these forms here, but if I go, obviously this is a 4th degree, and I enter the coefficients, basically negative 81, so it's literally x to the 4th plus 81. And when I go to solve that, yeah, see, that's literally what I get here. All right, any questions on this? I think it's pretty easy, pretty straightforward. All right, so, yeah, as I said, I'm moving the test back to Wednesday because that'll give us a little more time for review. So, the last test will be a take-home. So, well, you'll have the final exam in class. So, you'll have that one. Because it was negative 81, because W was negative 81, instead of positive 81, where the angle would be 0 degrees, negative 81 would be here. So that's how we get that. Yeah. All right, so as I was saying, the test has been pushed back to Wednesday of next week. So, yeah, we'll probably, we have, today's Wednesday. That way we can have, pretty much 2 solid days for review. Now, we're going to talk about vectors. Vectors are, believe it or not, actually not that bad. Might be the terminology that kind of flusters you a little bit. But we're going to see there's literally going to be no new math behind vectors. Quantities that are going to involve both a magnitude and a direction are called vector quantities, or vectors for short. You'll have magnitude but no direction. Those are going to be called scalar quantities, or scalars for short. So basically, we take a line segment to which a direction has been assigned. We'd call that a directed line segment. P is going to be your initial point, Q is going to be your terminal point, and we could denote this by PQ with an arrow above that. Now, the magnitude, which basically we've already, believe it or not, calculated magnitude. It's basically the length. But the fancier term for magnitude of a vector has 2 bars like that. And geometrically, a vector is going to be a directed line segment. See, this is going to be particularly helpful when you get into a course such as physics. Because what will happen there, yeah, you'll see that vectors are going to be a big thing when you get into physics, especially with things like free body diagrams. So generally, vectors V and W, we'll call them equal if they have the same magnitude and the same direction. Now in this case, yeah, 2 vectors V and W do have the same magnitude and the same direction. These 2 have the same magnitude, but different directions. These have the same magnitude, but opposite directions. And those 2 have the same direction, but different magnitudes. So equal vectors are going to have the same magnitude and the same direction. So if you're looking at this and thinking, boy, those 2 lines, U and V, have the same distance and the same slope. And if you're thinking that, you're thinking right. You're thinking absolutely right here. Basically, yeah, it has a slope of 4/3 and a magnitude of 5 if you calculated the distance between the 2 points. So we can break physics down into various vectors and determine what we would call a resultant force. Now, the multiplication of a real number k, generally an integer, but the multiplication of a real number k and a vector v is called scalar multiplication. We write this product k times v. Multiplying a vector by any positive real number changes the magnitude of the vector, but not its direction. And if you multiply a vector by a negative number, it's going to reverse the direction, such as in this third case. You multiply it by a negative, yeah, that's going to reverse the direction. So vectors can be scalar multiples. And believe it or not, scalar multiples actually come into play when you get into, if you get as far as linear algebra. So basically, if k is a real number and v is a vector, vector k times v is going to be a scalar multiple of the vector v. So basically, the direction can be changed if your k constant is negative. Now we're going to get what we have as resultant vectors. That's where it's going to get a little more interesting, so to speak. Basically, if we wanted to add 2 vectors, we would position them so that the terminal point of u coincides with the initial point of v. just like so here. And the resultant vector is simply going to extend from the initial point of u to the terminal point of v. And that's why we call it u plus v. And believe it or not, u plus, finding vector math, doing addition and subtraction, believe it or not, is actually very simple. You literally just add and subtract the components appropriately. Now, we're only going to be touching two-dimensional vectors in this course. I know some, like calculus sequences, I know I started college at Penn State. Yeah, that was a dumb move on my part. But when I took Calc 1 there, I was kind of in a little rough patch when I started Calc 2 when I transferred to Pitt for my second semester, because what had happened was they teach it very much vector based, and in Calc 1 I kind of missed all the vector stuff, so I kind of had to go back and do that, especially when I got into Calc 3, three-dimensional stuff. That was really where I had to go back. So you're going to have unit vectors, which, the direction will be along vector I, and if you notice that I is bolded, it almost seems contradictory, but this is not the imaginary number I. This is, vector I, and if you notice, it's bolded, and I'm going to do my absolute best to bold it. But that's why I write my imaginary I's with that funny-looking tail. Italicized, in a way, if you will. Yes. And vector J is your unit vector whose direction is along the positive y-axis. So basically, if we have vector V from the origin to AB, it's literally represented by AI plus BJ. The real numbers A and B are your scalar components, and A is your horizontal component and B is your vertical component. So we can find the vector sum, and then finding so since the vector sum, AI plus BJ, being a linear combination of your vectors I and J, the magnitude is given by, you guessed it, this. That's not new, is it? So what I want you to do is just give me a very rough sketch of the vector 3i minus 4j and find the magnitude. So if we want to find, let's do the rough sketch of this here vector. So 3i minus 4j. So basically it's, 3i and then minus 4j. So basically where it's going to end up is pretty much right here. So if we call it, the magnitude with the double bar, it's literally the square root of 3 squared plus negative 4 squared, which is ultimately going to be 5. That's all. All right, questions on that? Yeah, even if we ran through vectors today, that would only give us like one day to review. So basically, if you have a vector with 2 points, you can literally subtract the differences in coordinates. So I want you to write this vector in terms of I and j. So how do we do that? Well, it's real simple. So here's negative 2, 4. And that's where it's going to start. And 3, negative 8, it's going to go here. So basically from P1 to P2, I think the horizontal change is going to be positive, but the vertical change will be negative. So see if you can't. We continue this on here. So basically, you have 3 minus negative 2 for I plus negative 8 minus 4j. So you have 5I minus 12j. So that's the vector written in terms of I and j here. Now, if you changed P1 to the origin, yeah, it would wind up at 5 and negative 12. Now, I want you to find the magnitude of our vector. That'll be pretty easy for you. So what's the vector? I mean, what's the magnitude of this here vector going to be? 13. Because literally you take the square root of 5 squared and negative 12 squared, which gives you that. Now, if we have vectors v and w, basically v plus w means you add the horizontal and vertical components, and if you subtract them, you would subtract those or add the negatives. So if I wanted to add v and w, basically it would be 8 plus 5 times I plus 3 minus 8 times j, which is 13I minus 5j. So I want you to find the rest of these. That's easy enough to do. Basically, it's just going to be 8 minus 5 times I plus 3 minus negative 8 times j, which becomes 3I plus 11j. Or what you could do is you could just negate w, make it negative 5I plus 8j, and add them. Yeah, what I mean by that is you could have also done, v plus negative w. All right, so negative 5 times v is simply going to be negative 5 times 8I plus 3j, negative 40I minus 15j. Now for the last one, you do 5 times 8I plus 3j plus 3 times 5I minus 8j. You have 40I plus 15j plus 15I minus 24j, 55I minus 9j. All right, are there any questions about this? All right, so a unit vector is simply going to be defined as a vector whose magnitude is 1. So if we have a non-zero vector v, basically by taking the vector v and dividing it by its magnitude, now you'll likely get fractions here. So basically what you need to do here first is to figure out the magnitude of this vector v. Vector, that's very easy to do. It's literally just going to be the square root of -4 squared plus 3 squared, which is the square root of 25, or simply 5. So now, for the unit vector, where we divide it by its magnitude, it's literally just going to be -4i over 5 plus 3j over 5, or -4/5 I plus 3/5 j. So if we want to find the magnitude of this, now we know the magnitude of it's going to be 1. And this is the only time we're really going to do this. But if we take the square root of -4/5 quantity squared plus the square root of 3/5 squared, we're going to get 16 over 25 plus 9 over 25, which is going to be the square root of 1, which is 1. And that's how it all works. So yeah, you'll be expected to figure out a unit vector for this, such as this. Pretty easy, I think. All right, so one thing we can do with vectors is we can actually break it down into components. If theta is the direction angle measured from the positive x-axis to v, then the vector can be expressed in terms of its magnitude and direction angle as the magnitude times the cosine of theta times I plus the magnitude times the sine of theta j. Now, here's the thing. That looks pretty, it looks pretty similar here to that polar cis business we were doing. Well, as it should. So yeah, we can break it down into its components. Now, let's say the jet stream is blowing at 80 miles per hour in the direction of 60 degrees west of south. We can express the velocity as a vector in terms of I and j. Now, we'll round these to 2 decimal places here. Now, the luxury I'm going to give you here is, yeah, the angles will generally not even be unit circle angles. So, west of south, 60 degrees. Now, if you notice, here's the thing. So, yeah, 60 degrees. The vector in terms of I and j, both the coefficients of I and j are going to wind up being negative here. Now, a couple of ways you could actually do this. You could find the components, find the magnitudes of those 2 components that you see right there using that 60-degree angle. Of course, you'd have to kind of putz around with that, but believe it or not, there's actually a little bit better of a way to do this. You can literally, so if this is 60 degrees here, obviously this is 30 degrees. But what you can do is we can realize that the whole angle is 210 degrees. So basically, it will be 80 times cosine of 210 degrees I plus sine of 210 degrees J. We won't even need to round it to 2 decimal places for the sine here. But yeah, if we go to do, say, cosine of 210 degrees, well, first I want to quit this app. Yeah, if we do 80 times cosine of 210 degrees, we get negative 69.28 I plus, we want to figure out 80 times the sine of 210. And that's simply going to be negative 40. Negative 40J, or basically negative 69.28 I minus 40J. So, yeah, now what you could have done here is, maybe made a triangle and worked with different angle other than 210 degrees. But it's actually easier at this point to just figure out the angle between 0 and 360 based on the bearing. And that way you can get it straight up in your calculator. So, let's say we have two forces, F1 and F2, of magnitudes 40 and 100 pounds, respectively, acting on an object. So here's the thing. So let's say, so think about this for a minute. If two forces are acting on an object, like let's say, obviously, like let's say you want to push something, like push a car. Like obviously, if more than one person is pushing the car in the same direction, the resultant force of that is going to be better. But what if, let's say, I was pushing the car towards the door and you were pushing it towards me? It's basically a matter of which force is stronger. So we're going to get a resultant force out of this, and I don't think we're actually going to be able to finish this problem today. So here's the thing. F1 is 25 degrees east of north, like this. So basically, the angle in question is 55 degrees. F1, which is 40 pounds. Now, F2, 40 degrees east of south. This is 40 degrees. So yeah, like this would be 50 or 310 degrees if you went the whole Monty. And what you're going to do here, obviously, both forces are pushing it positively in the east direction. So the result is going to be that way. Now, based on the angle and the magnitude, I think this object is going to be heading down south. But we're going to do the math for this tomorrow. So that's it, everyone. All right, so what we want to do here is we want to go ahead and figure out the horizontal and vertical components of both of these forces here. So what we can do here is, we can form kind of two triangles here. For the first quadrant one, 55 degrees, it's going to work just as well here. So basically, how are we going to figure out the components? Well, basically, in order for us to figure out, F1I, that would basically be 40 times cosine of 55, and we'll call that I. And we'll round these to 2 decimal places. 40 times the cosine of 55 degrees, and that's going to be 22.94 I. And then F1J would be 40 times the sine of 55 degrees times J. Well, we want to figure out 40 times the sine of 55. Yeah, 40 times the sine of 55. That'll be 32.77 J. Now, our next order of business is to figure out the components for force number 2. Now, the horizontal component for force 2 is still going to remain a positive. Now, the vertical component will become a negative value. So we can easily figure that out. So, we see that is, 50 degrees below that. We could, of course, if we did sine and cosine of, say, 50 degrees, we'd have to manually add the sine here. But the other way you can do it is simply to treat it as a 310 degree angle. So basically, F2I would be 100 times cosine of 310 degrees times I. So when we use the calculator to figure that out, 100 times cosine of 310 degrees, 64.28 I. And then F2J, that's going to be 100 times the sine of 310 degrees J. And here's the thing. We know that's going to be a negative. So by taking it at 310 degrees, we know that it's going to be negative because, the sine of 310 degrees is going to be a negative value. Negative 76.6 J. So, now, of course, the other thing you could have done here is, like opposite and hypotenuse, If you had done, say, 100 times cosine of 50 degrees, you would have gotten 64.27. If you did 100 times the sine of 50 degrees, you would have gotten positive 76.6, but you have to know that that's negative. So this is why I always like to make the angle what it is, in this case 310 degrees. So now we're going to figure out the resultant force. And basically the resultant is where you simply add the vertical and the horizontal components. So 22.94 I plus 64.28 I. And the fact is both forces are going to be going positive in the horizontal, going to the right in the horizontal direction. So basically what's going to happen here is, we know the net resultant force is going to be a positive. So 22.94 plus 64.28, and that's going to be 87.22 I. Now, for the vertical components, you have 32.77J minus 76.6J. And that's going to be negative 43. So yeah, negative 43.83J. So we kind of figured that that's what's going to happen, even though what I should have done was drawn the arrow of force 1 much shorter than the arrow for force 2. You know, you're going to have a net resultant force. Again, this is something that's going to be very important when you get into physics. You know, when one or more forces act on an object, well, yeah, more than one force, you're going to have a net force, and that's what's going to cause it to move. And even net forces that, you know, it's harder to measure are basically like friction. It would be like trying to push something over a carpet. There would be a coefficient of friction, so to speak. All right, so now if we draw our resultant force, here's the thing. We're going to not only draw the resultant force, we're going to figure out the magnitude of said resultant force, and we're going to figure out what the net force is. So, yeah, 87.22I, negative 43.83J, and it's going to be this force here. Now, when it comes for the angle, basically, I'm going to be pretty wide open on that one. And here's what I mean by that. I probably should have made that a little bit bigger, but oh well. So the magnitude of the resultant force, you know, we could just call it R, would be the square root of 87.22 squared plus negative 43.83 quantity squared. And we get 97.61 pounds. Now, so yeah, that's going to be the resultant force. Now, what we want to do here is kind of figure out the direction here. Now, if we use this as our theta, so to speak, what we can do here, obviously set this up as a right triangle of sorts. This is 97.61, yeah, adjacent over, or no, not adjacent over opposite. So basically, you could take the tangent of theta equal to 43.83 over 87.22. So theta is simply going to be the inverse tangent of this ratio. Come on. All right, so when we do this, you know, 43.83 and divided by 87.22, and of course multiply that by 180 over pi, we get 26.7 degrees. But here's the thing, it's actually going to be negative 26.7. I'm not going to be so picky about the bearing. 97.61 pounds at negative 26.7 degrees, because technically you're going this way. Or if you add 360 to this, negative 26.7 plus 360, you would get 333.3. And here's the thing, 333.3 degrees definitely results in a positive horizontal component and a negative vertical component. So that's what you're going to get for that. All right, any questions? All right, well, as I said, we're going to have our test is going to be on Wednesday. So I'm going to basically, we're more or less going to have like 2 solid days for review here. So what I'm going to do is I'm going to just throw up some review problems. All right, so let's kind of draw this and see what's going to happen. So if we draw our little diagram here, so to speak. So force 1 is going to be 41 degrees east of the north line. So 41, and that means this is going to be 49 degrees. And this is going to be, 60 pounds. Now, the other one, 22 degrees west of the south line, and this is going to be 95 pounds. Not the best looking drawing here. So basically, we're going to literally have 2 forces kind of going in an opposite direction from each other. Not quite opposite though, but we're going to see what the net result is. But it's pretty clear that this is going to be a 49-degree angle, and this angle is going to be what? 200 and how many? 8? No, you were right. No, here's the thing. 248. Yeah, 248 degrees. Which is what? Yeah, I'm trying to get my weight down to, actually. 248. So, now that you know those, we can figure out the components. So, for force 1, you have 60 times cosine of 49 degrees I, and 60 times the sine of 49 degrees times j. So we figure those guys out here. And that'll be 39.36 I. And then the other one, 60 times the sine of 49 degrees, 45.28 J. So, and as you can tell, we knew both of those were going to be positive because, well, it's the first quadrant deal. Now for this one, you have 95 times cosine of 248I, or 248 degrees times I. And let's see what we get here. And we get negative 35.59 I. Now, already looking at this, when we add the horizontal components, it is going to be positive. It's going to head in the right direction here. And that's probably because, even though this was a stronger force, the angle of it kind of had an impact on that. So then you have 95 times the sine of 248 degrees times J. And that'll be negative 88.08 J. So now we need to figure out the resultant. So you have 39.36 minus 35.59, and that'll be 3.77I. And for the J's, 45.28 J minus 88.08 J. So we know that's going to be a negative value. Negative 42.8 J. So now, basically, we can draw it on here or make its own thing here, but there's 3.77 and here's negative 42.8. So we could figure out theta. I would like you to give me the theta as a positive angle or a bearing. It doesn't matter, but so we know that this angle, if we enter it in on the calculator here, this is 42.8 and this is 3.77. Tangent of theta, let's call it theta prime as well, is going to be 42.8 over 3.77. So theta prime, and looks like it's going to be an angle somewhat close to 90 degrees. Let's see what it is, if I can get this stupid thing to stay up. Times 180 over pi. So, wow, 84.9 degrees, or basically 85 degrees. So theta is going to be negative 85 degrees, or if we add 360 to that, angle could be to the nearest tenth, 275 degrees. So the resultant force, we didn't figure out the magnitude.
Anytime there's a zero in that part, does not play something like that.
Yep. So force, resultant force would be the square root of 3.77 squared plus negative 42.8 squared. And that's going to be 42.97 pounds. So basically, it's going to be 42.97 pounds at
South 5%.
Or two. Let's just call it 275. Yeah, 275. And 275 is fourth quadrant, and you can definitely tell.
I was feeding back the
bearing.
The bearing, since it gave it to us in a bearing.
Yeah, I gave it to you in a bearing, but basically, I'm not going to push the bearing for the final answer. All right, so that's what we're going to get for this one. So we keep looking. So now I'm going to give you a law of cosines question. So basically, you'd have a squared equal to b squared plus c squared minus 2bc times cosine of a. Let me just so basically, if you solve this one, I'm going to give you one version of this. Let's figure out the biggest angle, though. So in other words, you have b squared equal to a squared plus c squared minus 2 times a times c times cosine of b. Now, here's the thing. We already know all the sides. What we're trying to do is figure out what the angles are going to be. So that's easy enough to do. All we have to do basically is solve this for cosine of b. It's literally going to be b squared minus a squared minus c squared over negative 2ac, and that'll equal cosine of b. So cosine of b will be 17 squared minus 12 squared minus 14 squared over negative 2 times 12 times 14. And the really good thing is we can just use the calculator to kind of figure this out. You get 17 squared minus 12 squared minus 14 squared over negative 2 times 12 times 14. And that's going to be 17 over 112. So basically, we can take the inverse cosine of 17 over 112, multiply that by 180, and divide it by pi to figure out our angle. And measure of angle A or B is going to be 81.3 degrees. Now, we can figure out angle C with either law of sines or law of cosines. I kind of would prefer, I don't know why, but I like the law of cosines better. I don't know why, but I do. But here's the thing. If I have this equal to cosine of B, cosine of C is literally going to be C squared minus A squared minus B squared over negative 2AB. So, if I actually decide to go ahead and figure this out now, 14 squared minus 12 squared minus 17 squared, negative 2 times 12 times 14, that'll be 79 over 112. And if we do this, 79 over 112 times 180 divided by pi, that'll be 45.1 degrees. And we can easily figure out measure of angle A by doing a little bit of math here. 81.3 minus 45.1, and we get 53.6 degrees. Wait. Okay. A should be the smallest angle.
When you were doing the equation for cosine of cosine of C, the wrong number of B.
Oh. Yep, it should have been 2 times 12 times 17. Well, we could figure that. We can fix that right away. Yeah, it should have been 79 over 136. And then we just do this and take the inverse cosine of 79 out of 136. Multiply that by 180 and divide her by pi. And let's see what we got. 54.5 degrees. Yeah, that sounds like that'll make more sense. Because if we do 180 minus 81.3 minus 54.5, we get measure of angle A equal to 44.2 degrees. And that's where we'll stop. All right, so here's the deal. So let's do for Z1, and I think the R value is going to be 6, but let's just kind of figure this out here. Oh, come on, don't lag on me today. I mean, yeah, I could have just taken 3 root 3 and squared that, but well, why not? So yeah, it is going to be 6 here. So let's figure out the angle here. So it's going to be it's a negative horizontal value and a positive vertical value. So it looks like we're going to be in the second quadrant for this. So yeah, here's negative 3 root 3, and here is 3i. And if I call this, theta prime, I could call this, 3 root 3. I could call this 3. I could call this 6. But keep this in mind here. Whatever I get for this, theta prime, I have to subtract it from 180 or pi radians. So I could use literally any trig ratio that I want, but I'll just go with the classic tangent. Tangent of theta prime would be opposite over adjacent, 3 over 3 root 3. A lot of 3's here. And you don't have to rationalize that denominator or anything like that. Don't worry about that. But I'm going to take the arctangent of 1 over square root of 3. And in reality, I probably should have just made a for real fraction. I don't know what I was thinking, but that's going to be basically pi over 6 or, 30 degrees. So basically this becomes 6 cis 150 degrees. And I'll say you can have it in radian or degree mode. I mean, for this, I'm not going to be overly picky on that. And the good thing is Z2 will be a first quadrant angle. So let's see if we can't figure that out real quick. And what was that? 1 plus I root 3. So that's going to be square root of 4 or 2. And let's see here. 1. So yeah, and the luxurious thing is the angle in question is going to be a first quadrant, so we don't have to putz with anything, which is kind of nice. So basically, tangent of theta, I'll call it theta sub 2, I should have called this theta sub 1, is going to be root 3 over 1. So basically, I'll take the inverse tangent of literally square root of 3. Don't want to do that. And we get, I think this is pi over 3 or 60 degrees. So this becomes 2 cis 60 degrees. All right, now that we have these in polar form, you can figure out the product, the quotient, and z1 to the 4th power. So I'll give you a couple of moments on that. All right, so let's figure out z1 times z2. So basically, that's literally r1 times r2 cis theta 1 plus theta 2. And of course, you're going to get these formulas on your test, so it's not like you have to memorize them. So R1 and R2 are 6 and 2. 6 times 2, cis 150 degrees plus 60 degrees. So that's going to be 12 cis 210 degrees. So the other thing that I want you to do with this, though, is let's figure this out in rectangular form. Now, if you notice, 210 degrees, that's going to be a third quadrant angle. So both the real and the imaginary part shall be negative. And that's root 3 over 2, or negative root 3 over 2. And sine of 210 is negative 1/2. And basically, you're going to get negative 6 root 3 minus 6i. So that's the polar form. And this here is the rectangular form. All right. How about I give you a couple of moments on that quotient? Now, of course, I'm going to give you the formula, and it's literally going to be the quotient. And instead of adding the angles, you literally just subtract them. So what we've got here is 6 over 2 cis 150 minus 60 degrees, or 3 cis 90 degrees. And that as rectangular is just going to be 3i. Yeah, because sine of 90 degrees is 1. Cosine of 90 is 0. All right, now for last part of this bad boy, z sub 1 to the 4th. And that's basically going to be, r1 to the 4th times cis of 4 theta. All right, so basically this is going to be 6 to the 4th times cis 4 times 150 degrees. So that's going to be, 6 to the 4th, that's going to be a large number. 1296 times cis of 600 degrees. Now, I'm going to be specific and say you've got to give me the angle that's between 0 and 360. So all you have to do in this situation here is subtract 360. So that's going to be 1296 times cis 600 minus 360 is 240 degrees. Now, since we know that that's going to be a third quadrant angle, we know for the rectangular form, it's going to come out, both are going to be negative. So if we do cosine of 240 degrees, that's going to be negative 1/2. And this will be minus I times root 3 over 2. So, 1296 divided by 2, that's 648. So, negative 648 minus 648i root 3 for the rectangular form. law of cosines. And law of cosines isn't really going to help us here. So basically, I'll just give you the law of sines as well. So let's fill out what we know. All right, so basically we have a full ratio here and one here. So all you have to do at this point is set these two equal to each other, and you're going to get the sine of C equals something. So basically, it's going to be this whole ratio here. So yeah, you have 28 times the sine of 43 degrees over 20, and it'll be 0.9548. Well, you take the inverse sine of that, and you're going to get two values. Well, you would always get two values in a case like this. But what's going to happen is there might be a case where it wouldn't be the ambiguous case, where the angle will just be that too large. But if we take the inverse sine of 0.9548, 0.9548 times 180 over pi, 72.7 degrees. Or if we took 180 less that.
If I round to the nearest degree, is that fine?
No, I want it tenths. Let's keep it as tenths. And the measure of C could also be 107.3. And since 43 and 107.3 don't go beyond 180, this is the ambiguous case. So you get to figure out, let's see what we've got here. Now, one of those angles was 43 degrees. So basically, measure of A is going to be 43 degrees no matter what. So we get to figure out the missing angle in each case. 180 minus 43 minus 72.7. And let's see here, 180 minus 43 minus 107.3, 29.7. So yeah, for this first case, yeah, you're at 64.3 degrees. And then for measure of angle B, in this case, we are at 29.7 degrees. So we have A and C here. We just need to figure out what B is going to be. Side B is going to be. Because, A is 20 miles, C is 28 miles. So if you do 20 over sine of 43 degrees equal to B over sine of 64.3 degrees, and solve this bad boy, B will be basically 20 times the sine of 64.3 degrees over the sine of 43 degrees. Come on, 64.3 degrees over sine of 43 degrees. And that'll be 26.4 miles. And if you remember, angle B is the middle angle in this case, and it's going to be the middle side. Now, if we figured out B in this case, that would be 20 times the sine of 29.7 degrees over the sine of 43 degrees. So I'll just do this because my calculator affords me that luxury. I get 14.5 miles. And that's going to be the smallest side because it's opposite the smallest angle. Okay, so with that in mind, I'll give you a root question. What I'm going to do here is figure out the polar form of this. Now, that's going to be a third quadrant angle here. And I think this is going to be 64, but let's double check it. Not that one. Yep, 64.
Is there any case where that would not result in a whole number?
Oh yeah, plenty of cases, but I would not give you one. So yeah, it's always a possibility that this would not result in a whole number, but for simplicity purposes, it's going to. I will not throw I don't like throwing curveballs at myself. You ever been hit by a baseball? It hurts. Yeah.
In some ways, getting hit by a softball is worse than getting hit by a baseball.
All right, so it should be right around here. Now, probably more like here. So, yeah, there's going to be theta. So, we can, a little off on the mark here. So, yeah, 32, and this is 32 root 3. If I call this, theta prime, tangent of theta prime is going to be 32 root 3 over, not root 3, but 32. So I just take the inverse tangent of root 3. And that's going to be 60 degrees. So basically, theta prime will be 60 degrees. But because this is a third quadrant angle, you add 180, so theta will wind up being 240 degrees. So basically, W will be 64 cis 240 degrees. Now, we're going to find the 6 sixth roots. And this is, again, why the R is going to result in a whole number here. So there's going to be, actually that shouldn't be N, this should technically be a K. The sixth root of 64 which we should know is 2, times cis of 240 degrees plus 360 degrees K over 6. Now, what we can do with this basically is we obviously need to figure out, the K values starting at 0. But what we could do here, obviously the 6 root of 64 is 2. And it'll be cis 240 over 6 will be 40 degrees plus 60 degrees K. And this is why I'm only going to be wanting the roots in polar form here, because converting these to rectangular is going to be very fugly, to say the least. So when K is 0, you have 2 cis 40 degrees. When K is 1, you have 2 cis 40 plus 60, which is 100 degrees. When K is 2, you're at 2 cis 160. You're going up by 60 degrees each time. When K is 3, that's 2 cis 220, 2 cis 280, and 2 cis 340. All right, so yeah, we're not going to convert these to rectangular form again because it's going to be some really nasty thing. So this, my friend, all right, so basically if you remember, x will equal r cosine of theta, y will equal r sine of theta. So what happens here basically is you replace the x's with r cosine theta and plus 3 quantity squared, and you replace the y's with r sine of theta. And then basically you'll do the expansion, and there, boys and girls, is a reason why the other side of this is going to equal 10. Because left-hand side is ultimately going to equal 10 here. So you have r cosine of theta plus 3 times itself. So then you have r squared cosine squared theta plus 6r cosine theta plus 9. Oh, come on. Almost looks like a smiley face. R squared sine squared theta plus 1 plus 2, so plus 2 r sine theta plus 1 equals 10. Now if you notice, 9 and 1 is going to be 10. What you can do right now is you can just kind of remove that, and you can take out r squared, from cosine squared theta plus sine squared theta plus 6r cosine of theta plus 2r sine of theta equaling 0. Well, cosine squared theta plus sine squared theta is what? 1. So you have r squared plus 6r cosine theta plus 2r sine theta equals 0. So now you get to factor out an r. Plus 6 cosine theta plus 2 sine theta equals 0. So basically r equals 0, that's one of them. R plus 6 cosine theta plus 2 sine theta will equal 0. So basically we move that over here. It would be negative 6 cosine theta minus 2 sine of theta. I'm not going to have you graph one by hand. All right, so here's the thing. If we set this up with law of sines, you have A over sine of A equal to 16 over sine of B equal to 9 over sine of C. Oh, sine of 51 degrees. So 16 times sine of 51 degrees will equal 9 times sine of B. Divide her out by 9. And sine of B is going to equal this. Well, let's see what this is. Let's see. Yeah. 16 times the sine of 51 degrees over 9. And that's 1.3816. And since the sine of an angle is obviously greater than 1, in this case, we literally have no triangle. So you kind of lucked out on that one. Curious. Of course, I would say of the resultant. All right, so what we'll do is we need to figure out the components here. So 32 degrees east of the south line, and it's probably not the best looking angle here for 32 degrees, but this is, 289 miles per hour at, let's see, 270 plus 302, 302 degrees. And let's see here, 12 degrees east of north. And let's see, this is 78 degrees. So basically, we need to figure out the horizontal and vertical components of both. Now, both horizontal components are going to go in the same direction here, but the vertical components are not. Because, you have the wind going this way, and they're hightailing it to some country down in South America so that they don't get caught. I mean, you think about it, what kind of money? So, let's see what we got here. So if we do 79 times cosine of 78 degrees, let's see what that's going to be. And we'll round all this to 2 decimal places, 16.43 I. And we know the vertical component is going to be positive. If we do 79 times the sine of 78 degrees, plus 77.27 J. And you don't even necessarily have to do it in terms of I and J if you don't want to. Yeah, I just think it's a little easier to do it this way. So for the plane itself, you took 289 times cosine of 302. Uh, 153.15 I, but we know for the J, negative 245.09 J. So for the resultant, basically you add your I's and your J's here, and what's going to happen is obviously the I's will be positive. So if you add the 16.43 and 153.15, we get 169.58 I. And if we do 77.27 minus 245.09, we get minus 167.82 J. Wow. It's going to be pretty consistent here. So now, basically, if we draw this out, it's going to look something like this. 169.58, 167.82, and we call this theta prime, opposite over adjacent. So tangent of theta prime will be 167.82 over 169.58. So we take the inverse tangent of that. And we get that, and I'll convert that to an angle. I'll convert that to degrees. 44.7 degrees. But I can subtract that from 360, so the angle that I really want will be 360 less that, or 315.3. Now, for the magnitude, all we got to do is take this, and let's see what we get for that magnitude. Come on. 5/8 quantity squared plus negative 167.82 squared, 238.58 miles per hour. Yeah, in reality, would a plane be flying if there were winds of 80 miles an hour? I don't know, but yeah, knowing Harry and Marv, the bumbling burglars, they probably would. Oh, I think Marv actually does have a bit more of a heart in that. Good thing is, yeah, this one we can use very simple law of sines. No way for the ambiguous case to happen here. Measure of angle C is going to be 26 degrees. So you have A over sine of 85 equal to B over sine of 69 equal to 7 over sine of 26 degrees. So basically we need to figure out what A and B are going to be. And so let's do that here. I'll set these two equal to each other. B times the sine of 26 degrees equals 7 times the sine of 69 degrees. We divide out by the sine of 26 degrees and use a calculator to figure that out. I'm going to use one of these because, I don't know, I just feel like doing it. Let's see, yeah, 7 times the sine of 69 degrees over sine of 26 degrees. Oh, wrong one. And that'll be 14.9 meters. Now I'll set this ratio equal to it. Set the first and the second one, first and the last one equal. It doesn't really matter. A times the sine of 26 degrees equals 7 times the sine of 85. So divide out by sine of 26. And we figure out what that one's going to be. 7 times the sine of 85. There we go. And this will be 15.9 meters. So now, if we want to figure out the area, we have to first figure out what S is, and that's basically A plus B plus C divided by 2. So that's going to be 15.9 plus 14.9 plus 7 divided by 2. And you'll be given these formulas here. And you're going to get 18.9 for your value of S. Now, the thing is, rounding this to the nearest tenth, this answer might not be as close as you think. I mean, the thing is, I'm going to allow for wiggle room. S minus B, and then S minus C. And so basically, take square root of 18.9 times 18.9 minus 15.9 times 18.9 minus 14.9 times 18.9 minus 7. And we get 51.95 or 52 squared meters. All right, not bad. All right, so we'll have time for kind of one more question. Now we know that this is going to throw us into the third quadrant here. So let's see here. It should be something probably like this. Oh. So we need to find the magnitude. And the magnitude of this is going to end up being what? 8. Yep. All right. So now let me think of something. Give me one. Yeah. So yeah, your R value should always be an integer. I mean, there's definitely a possibility where it will not be an integer, but not in this class. I'm not opening up that Pandora's box. So yeah, let's call this theta prime, like Coach Prime. And because I'm so bored with tangent though, you know what? I'm going to do sine of theta prime equals opposite over hypotenuse. So 4 over 8, well, that's 1/2. The inverse sine, by the way, you will get a unit circle. I don't even know why I pretended to, yeah. So that's going to be 30 degrees here. But the angle in question, Z will be 8 cis. This is 30 degrees here, but you add 180, so you have 210 degrees. Hence, Z to the third will be 8 to the third times cis 210 times 3. Now, I will also add that give me the angle between 0 and 360. So let's see here. This is 512 cis 630 degrees. But let's subtract 360. And we get 270. Oh, wow. I made this actually way too easy. Because here's the thing. 512 cis 270, 512 times cosine of 270 plus I sine of 270. Well, cosine of 270 is what? And sine of 270 is negative 1. So it's just literally negative 512i. And that, ladies